Yeah.
Jay sir, good morning.
Good morning, sir. Janendra, sir, good morning. Zurek, sir. Rahi, sir, good morning. Sir.
Good morning.
So let us start. Thanks for your blessings which are with us. This is a very modest effort to connect the technology with the fundamental understanding about the quantum science, which is, I think, the most important thing for the new and young generation. Although we started it 4 years ago. And with the blessings of Professor Jain, Professor Deshmukh, Professor S.C. Verma, and our own Professor Y.K. Vijay, Professor P.K. Ahluwalia sir, Professor K.S. Sharma sir, we were doing some subtle efforts. After the initiation and motivation received from Professor Tarun Swaradip, who is the director Raman Research Institute, last time when he was the chief guest and keynote speaker, he said that we should go in a big way for this kind of effort because this is what is needed. The, the quantum science is the fundamental language of nature, and it should be understood by the students at the very early stage. And this kind of platforms can sensitize them in a very effective way. So, in the continuation of that particular effort, we are holding this particular meeting. Professor Ahluwalia sir, are you there, sir? Hello. Professor Ahluwalia sir is not there, I think. So, I will welcome. We will start right from the keynote of today's event. Professor Janendra Jain sir will be speaking. As we know, Professor Jain is the Wolf Prize winner in physics, and he is the Ivan Pug University Professor and Irving W. Mueller Professor in the Physics and holder of Eberle Family Chair, Penn State University. Welcome, sir. Professor Jain is a
Thank
renowned,
you.
sir. Professor Jain is a renowned Indian American theoretical physicist. Was awarded the 2025 Wolf Prize in Physics for his pioneering theory of composite fermions, a transformative breakthrough in the understanding of two-dimensional electron systems under strong magnetic fields. Currently serving as Ivan Pug University Professor and Irwin W. Mueller Professor of Physics and holder of Eberle Family Chair at Penn State University, Dr. Jain's work has opened new frontiers in condensed matter physics and quantum technologies. His most celebrated contribution, the discovery of composite fermions, introduced a new class of quasi-particles formed when electrons couple with magnetic flux quanta. This theory offered a unified explanation for both the fractional and integral quantum Hall effects, connecting two Nobel Prize winning phenomena and reshaping the theoretical landscape of low dimensional quantum systems. Born in Rajasthan, India, Dr. Jain has an illustrious career in physics. He earned his bachelor from Maharaja's College, Jaipur, a master's from IIT Kanpur, and completed his PhD at Stony Brook University in 1985. He held postdoctoral positions at the University of Maryland and Yale before joining the faculty at Stony Brook and later moving to Penn State in 1998. In recognition of his work, he received the Oliver E. Buckley Prize in 2002. His contributions continue to impact the development of topological quantum materials, which are very important for quantum sciences and technologies, with application in quantum computing and high performance electronics. We welcome Professor Jain as the keynote speaker and thank him because it is too late. Sir, I'm sorry, first of all, for bothering you at this time, but there was no other way. We wanted the students of India to listen to you. We want them to get inspired from a modest background. If you can inspire, if you can effect two Nobel Prizes at a time, I think the next Nobel Prize winner from India is in front of us. Friends, let us welcome Professor Jain. Sir, you may start your presentation.
Okay, thank you. That's a very generous introduction, Professor Sharma, and thank you for giving me this opportunity. Let me share my screen. Uh, so, okay. So it's always, so you can see my screen, correct?
Yes, sir. Yes, sir.
Okay. So it's always a pleasure to be in Jaipur, even if virtually. And again, thanks for giving me this opportunity. So I have a very simple presentation, which I will try to finish within half an hour. Okay. Uh, so when you see this jumble of letters or symbols in front of you, you may think it's just nonsense, it has no meaning. But that's not true. It's actually an encrypted message. Uh, if you had the key, the encryption key, you can read this. Uh, so to me, so theoretical physicists all have different approaches. But to me, theoretical physics is not that different from this. So nature gives us lots of different facts, and at first they seem rather unrelated. They all seem puzzling, and we don't know what the nature is trying to tell us through those facts. But the job of a theoretical physicist is to kind of crack the code, is to figure out what is the encryption key, or in other words, what is the underlying principle that would impose some sort of coherence over all of those facts that seem disparate in the beginning, and show that they are part of a single conceptual structure. And, so that way we understand what the nature is trying to tell us. Um, Now, Professor Sharma mentioned technology. So one could ask, what good is fundamental physics? What's the point of understanding all these facts of nature? Well, Max Planck put it very succinctly and very nicely. Insight must precede application. So if we want to use nature to better our lives, first we have to understand nature. And history is filled with examples where discoveries were made just for the sake of understanding nature, but later they turned out to be extremely important for our everyday lives. So, for example, the development of the theory of electrodynamics, which took place by people like Faraday and Maxwell in the middle 19th century, was just for the sake of discovery, but now this has kind of permeated every single aspect of our lives, and similarly, you could ask Albert Einstein, why are you studying general theory of relativity? What good is it? But now our cell phones, the GPS technology in our cell phones, it solves the general theory of relativity equations to accurately locate our positions. So I'm going to tell you here that the system of, so I keep getting these things at the stop share. Okay, I don't know how I get rid of this stuff at the top. Okay, so I'm going to tell you that the study of systems of electrons confined to two dimensions and exposed to a very strong magnetic field has taken us into an astonishing new quantum mechanical universe where things happen that we could not have imagined in our I mean, they cannot happen in our three-dimensional world actually. And in particular, this universe is populated by particles which are unlike any other particles. They are particles like electrons, which are bound to flux quanta, magnetic flux quanta, and in particular, they give rise to even more exotic particles. Um, and in particular, uh, it's you know, giving meaningful to me because this is the year of 1879, almost 150 years ago. Edwin Hall was performing resistance measurement uh, in the presence of a magnetic field. So, how the resistance behaved as a function of the magnetic field. So, the ordinary resistance, which is a voltage along the current path, he found to be more or less independent of the magnetic field. But then he noticed that there is also a voltage across the current path, which is now called the Hall voltage. So he defined a new resistance called the Hall resistance. That's VH divided by the current. And he found that it goes linearly as a function of the magnetic field. Okay, so there are two resistances. One is flat, the other goes linearly. And this actually can be understood from a straightforward application of the Lorentz force law. And this is something that has been, tested in thousands of labs across the world, you know. But things changed in 1980. So, I should also say that we are all creatures of, or we are all products of our circumstances. And I joined my PhD in 1981. And just 1 year before my PhD began, there was an important discovery that set the course of my career. And it depended on the availability of two-dimensional electron systems. So at that time, the two-dimensional electron systems were produced by taking a very thin slice of a semiconductor, which is shown in the gray color here. Uh, and if one catches electrons in this thin slice of semiconductor, the electrons can move only in two dimensions. They cannot move in the perpendicular direction. Uh, Now, of course, we all know about graphene, which also is a two-dimensional crystal of carbon atoms, uh, which which also hosts two-dimensional electrons. Uh, Sharma ji, I'm getting this thing at the top. I, I keep getting these messages. How do I get rid of those? Just,
What messages are you getting, sir? Joining
you
के?
know, people
Oh,
joining and so on. I'm
we
getting all
will
those.
we will stop, sir. We will stop. You please continue. We will stop.
Okay. So in around 1980, I mean, so these systems, these two-dimensional systems are actually, they're extremely important to us because they are an integral element of transistors. These are called MOSFETs, and all our phones and computers have them. Uh, so in 1980, Klaus von Klitzing, he repeated Hall effect measurements in two dimensions on these two-dimensional systems. So at small magnetic fields, the ordinary resistance was more or less constant as a function of B, and the Hall resistance rose linearly. So this is exactly as we expect. But when he went to higher magnetic fields, he saw something very amazing. He found that the Hall resistance takes only some special values. So it jumps from one value to the next value, which means it is quantized. And moreover, he found that the value of the Hall resistance on these in these regions is universal. So, typically the resistance depends upon the size and shape of whatever sample. So if you make the length twice as long, the resistance becomes twice as big. But here, the Hall resistance here, it does not depend on the size or the shape. You could take a sample which is a mile long or a millimeter long. You find that the Hall resistance is given by h divided by an integer times e squared, where h and e are fundamental constants, and the integer is denoted I here. So, moreover, he found that whenever the Hall resistance is quantized, the ordinary resistance essentially goes to zero. So it's exponentially small. So this phenomenon is called the integer quantum Hall effect. It's quantized Hall effect, and the quantized values are defined by this integer. And the phenomenon was so surprising that he very soon received Nobel Prize for it in 1985. So what is happening here? Well, at very low temperatures where this experiment was performed, we minimize energy. So let's recall there are two types of energies: kinetic energy and interaction energy. Um, Due to quantum mechanics, due to the magic of quantum mechanics, in a magnetic field, the kinetic energy takes certain special values. So it cannot take a continuum, but it takes only some discrete special values. In other words, the kinetic energy is quantized. And some of you may know that these are called lambda levels. So let's first forget about the interaction and minimize the kinetic energy. So typically you get a situation like this. So the lowest kinetic energy level is here in this picture. Lowest one is full, and the second one is partially full with electrons. Uh, in this situation, there are several ways I can put these electrons in the second kinetic energy level. But there are some special situations when we have an integer number of filled levels as shown here. Uh, and here the solution is unique. So we know precisely what the state is. There's a unique state. And it turns out that this underlies the explanation of the integer quantum Hall effect. It occurs, this effect occurs because in this region, the state of the system is given by this very simple, unique state, which contains an integer number of field levels. And I should say that there is a topological interpretation of this, which was developed by Haldane and Thouless, for which they received the Nobel Prize around 10 years ago. Now, in this field, and I think that's true of pretty much any field in physics, whenever we feel we understand things, nature, presents another mystery. And in this case, it happened only a couple of years later. So these three gentlemen, they went to yet higher magnetic fields, and they saw a region where the Hall resistance was constant, but in the denominator, we have a fraction instead of an integer. The first fraction to be observed was 1/3, and as soon as this was observed, it created such a huge excitement that many experimentalists started to look closely in this region. And as I'm going to show you, they saw many, many more fractions. And this led to a Nobel Prize to two of these in 1998. So this is referred to as the fractional quantum Hall effect. Uh, so uh, here you see many more fractions. So this is 2/5, this is 3/7, 4/9, and so on. And in the best quality samples, there are maybe about 100 fractions. This shows the resistance as a function of the magnetic field. And every time you see a minimum in the resistance, uh, there is a flat region in the Hall resistance where it is quantized at some fractions that one can read off. So the fractional quantum Hall effect is, I would say, among the most stunning manifestations of quantum mechanics at the macroscopic scale. It is one of the most striking mysteries that nature has presented in quantum condensed matter. And I would also say that this is perhaps the most beautiful single trace in physics. And I guess it's not only beautiful experimentally, but also the underlying explanation of it, as we will see. Like I was telling you in my first slide, all these fractions, they first appear to be disconnected, and we don't know what is happening here, but we have to figure out, once we figure out what's happening here, we'll see that they all can be understood as part of a single framework. Okay, so let me also say that in this region, we don't have full levels. So electrons are not able to, they only partially occupy the lowest level. And in this case, now we must deal with the interaction energy of electrons, and that actually is a much, much more complicated problem. In fact, this, you may say, is the most strongly correlated state ever, because there is no kinetic energy. And these days people talk about flat bands in many situations, and we know whenever bands are flat, which means the kinetic energy has been quenched, the interaction energy dominates the physics and gives rise to lots of beautiful physics. Okay, so uh, the question is, what's the question? We have to figure out what the question is. In fact, I would say that the art of theoretical physics is to ask the right question at the right time. And if the question is properly developed, refined, and sharpened, it often has the answer in it, or at least it points the way to the answer. So you may say, well, the question could be, what's the physical origin of the fractional Hall effect, or what's the organizing principle, or what's the mechanism? This is basically the same question asked in three different ways, and it's not particularly illuminating. So let's take another look at the experiments. And you would notice that there is something very strange about this picture. And to bring that out clearly, let me erase all the numbers from this figure like this. And then you will notice that you cannot tell integers from fractions. So, this same figure contains both integers and fractions. And in a qualitative sense, you cannot tell the two apart. So it seems rather strange that we understand the integer quantum Hall effect very well, but we don't understand the fractional Hall effect. So you would think that there must be there must be a deep connection between the two. So you ask, can we unify these two effects? Well, what does that mean? Well, that would mean we have to understand the fractional quantum Hall effect as the integer quantum Hall effect. But then you ask, what? Integer quantum Hall effect of what? Well, there must be some weakly interacting emergent particles in the fractional Hall effect. So the question that actually gives a clue is, what are the weakly interacting emergent particles of the fractional Hall effect, in terms of which we can understand it in terms of integer Hall effect of those particles. Okay, so let me tell you what these particles are, but before that, let me say that, of course, this was not this this insight did not come in vacuum. There was a lot of really amazing theoretical work and lots of incredible experiments that uh, prepared the ground for it. But when I was a postdoc a long time ago, I suddenly realized that if I introduced a new kind of particles called composite fermions, then I could understand the fractional quantum Hall effect as the integer quantum Hall effect of composite fermions. A composite fermion is the bound state of an electron and an even number of magnetic flux quanta, as shown here. A flux quantum is defined here. And in some, you may say that composite fermion is the encryption key for the fractional Hall effect. The simple physics of composite fermions is that if you take strongly interacting electrons in a strong magnetic field, they each capture 2 or 4 or 6 flux quanta to turn into composite fermions, which then see only the residual magnetic field, which is denoted by BCF. So the key difference between electrons and composite fermions is electrons see the external applied magnetic field, composite fermions see a much reduced magnetic field. And in fact, one can show that the integer quantum Hall effect of composite fermions produces fractional quantum Hall effect of electrons at these fractions where p and m are integers. Uh, so just like we understand the integer Hall effect as filled levels of electrons, we can understand the fractional quantum Hall effect as filled levels of composite fermions, as shown here. Um, the composite fermions are very complicated particles. So, what I'm calling flux quanta are actually vortices. And so they are some collective bound states of all electrons. So composite fermions are unlike any other particles known previously. So it's a legitimate question to ask, well, do they exist? And if so, in what sense do they behave as particles? Uh, Now, of course, the experiments have the final word. The theory needs to explain experiments and make non-trivial predictions. Uh, so in this case, it turns out that the composite fermion theory successfully predicts or explains thousands of facts in a completely unified fashion. I, of course, won't have time to go over these. I'm just going to show in this talk that it explains, and I'm just so I won't have time to talk about the other successes of the composite fermion theory. So the prominent fractions appear in some certain sequences. They appear in sequences because they all uh, originate from the sequence of integers. So one sequence is p over 2p plus 1. This comes from composite fermions which have two flux quanta bound to them. And in this figure, they have seen 10 members of this sequence. Similarly, there are sequences that go as p over 4p plus 1 or p over 4p minus 1. These originate from composite fermions carrying 4 flux quanta, and several members of these two sequences have been observed. In fact, in the best samples of the day, they have seen like 14 or 16 members of these sequences, p over 2p plus 1 and p over 2p minus 1. There should have been a minus here. Uh, Composite fermions carrying 6 and 8 flux quanta have also been observed experimentally. Of course, so all of the experiments I showed up to now, they were on gallium arsenide quantum wells, but there's nothing special about them. One could take a monolayer graphene or a bilayer graphene, and precisely these sequences appear in those. In fact, very recently there has been another twist in this field, which is that fractional Hall effect has been seen at zero magnetic field. And this is something that just came out of nowhere. If 5 years ago somebody had told me that, fractional Hall effect can be seen at zero magnetic field, I would have betted against it. But anyway, it turns out that there also they see precisely these sequences experimentally. Uh, and in fact, one can compare the fractional and the integer Hall effect. So here what I've done is I have taken this panel and repeated here, except that in the top panel, I'm showing it as a function of B as seen by composite fermions carrying two flux quanta. And you would see that 1/3, 2/5, 3/7, 4/9, they align with 1, 2, 3, 4, 5, 6. So this looks just like the integer Hall effect of certain particles, as the composite fermion theory predicts. Uh, so over the years has grown into many, many different directions. Not only has their integer Hall effect been seen, but their superconductors, their fractional Hall effect, their bilayer states, their metallic states, their crystals, all of them have been seen. And many, many of their properties have been measured. So if you're interested, I encourage you to consult one of these books here. Uh, Now let me just end my talk by spending a couple of minutes on how this fundamental physics might lead to technology. Um, so one of the states that I mentioned on the last slide was superconductivity of composite fermions, where composite fermions pair up, opening a gap. And it turns out that this uh, supports an even stranger particle. This is called a Majorana particle. Uh, Majorana is so strange that if you take two Majoranas, so this is supposed to be M, so this is one Majorana, this is another. If you combine two Majoranas, it could give you either one composite fermion or a zero composite fermion. So this can be simultaneously one or zero composite fermion. It's something like Schrodinger's cat, which can be simultaneously dead or alive. And it has been proposed that this property can be used to make a qubit, a quantum bit, which would lead to fault-tolerant quantum computation. So this is not just an idea. Microsoft has spent like $1 billion to try to realize this program. So they are using Majoranas not in fractional Hall systems, but they're using Majoranas uh, that are produced at the ends of semiconductor nanowires. So it's very similar physics. Uh, I should say, so they have earlier this year in February 2025, they unveiled their chip called Majorana 1. But I should say that there is quite a bit of controversy here and it's not fully confirmed. More work will need to be done before this idea is confirmed. Uh, Let me just end my talk by reading the concluding part of this article editorial that appeared in physics, Nature Physics just last month. So it says, perhaps another platform might win the race to perform the first topologically protected quantum computation. But for now, we would not bet against the dark horse of quantum Hall systems getting there first. So if this becomes a reality, this would be another really thrilling chapter in the story of fractional Hall effect and composite fermions. So let me just end my talk by thanking my students. I've had the honor of and the pleasure of working with many, many brilliant, their hard work, which has established the reality of composite.
Thank you very much, sir, for
Okay,
for your
I
blessings
noticed
and a
I
very
finished it.
nice talk. It is very inspiring. Your good friend, Professor Y.K. Vijay sir, is with us. Sir, would you like to thank Professor Jain?
Well, it's a great honor for us, sir, to listen to you repeatedly. It's a excellent science which is growing, the
Okay.
theoretically and experimentally, which can shape the world. So, what I can say that the behavior of nature in quantum science, you can realize and control them. In fact, what I realize is really in low dimension, when the electrons are confined in a small region, still you can control the uh, development of modern high speed computers like quantum computing. Okay, the probabilistic approach, the uncertainties which are the bare need of entanglement, bare need of quantum mechanics and quantum theory, which you can realize in a condensed matter. So it's an excellent piece of work. Looking forward to the coming Nobel Prize again.
Oh, come on. Please,
Okay,
please.
best of luck. All right.
Thank you.
It's really inspiring. Once the device comes in application, then you realize how important is the theory, okay, which you work to explain the results. Thank you so much for inspiring the young generation. All right. Globally, it's excellent.
Thank you,
Regards.
sir.
Thank you.
So one achievement I think for today's meeting is that Professor Jain met Professor Farahi and Professor Jurek also. I
Great,
think
great.
Professor Farahi has interacted as a teacher with Professor Jain. Some day at some interaction he was in interaction with Professor Jain. So
Yeah,
it is always, yeah.
Professor Farhi probably doesn't remember, but this was, so I spent a sabbatical year at MIT that I think was in 1997 or 98.
So,
And I took one of his classes on gravity. So you taught a lecture, you taught a course on gravity at that.
That was a great class to teach, and I remember how much fun we all had.
so
So yeah, it was great having you there.
actually, teacher doesn't remember because lot many students are there. But there is one of the students like Professor Jan who becomes like you. So it is the great achievement of a teacher that he inspires people who actually further the human knowledge.
I
So
will not take credit for him.
no, sir, we give credit to you and Professor Jain also. Sir, it is very late at there, and still you are with us, inspiring the young generation. So, if you permit, sir, we can next request the speaker.
Sure.
Sir. The next speaker is Professor Catherine M. Jurek, Professor of Theoretical Physics at Caltech. Ma'am, are you there, ma'am?
Yes, I am.
Thank you, ma'am, to you also to be with us to inspire the students of India and globe, because it is very important that students adapt their quantum science as a friend of them, because it is very counterintuitive. And the last time when we had a meeting with the principal scientific advisor of Government of India, he said that we physics teachers have a great responsibility of on our shoulders, because the technologists, the engineers who take the physics classes in the first or second year of their BTech degrees, those must be taught or interacted in such a way that students love quantum science. Then only they will be able to apply. So let us welcome Professor Kartin M. Jurek, who is a distinguished theoretical physicist at Caltech, known for her innovative work at the intersection of particle physics, cosmology, and astrophysics. Her research addresses some of the most profound questions in physics, particularly the nature of dark matter and the search for a theory of quantum gravity. Professor Jurek is widely recognized for her development of hidden valley or hidden sector models of dark matter, which suggest that dark matter may reside in an unseen sector with entirely new intersections, revolutionizing the scope of dark matter research. Her work bridges theory and experiment, contributing to novel detection methods using materials such as superfluid helium and superconductors to search for light dark matter particles. In recent years, she has expanded her research to explore how quantum gravity might leave measurable imprints in tabletop experiments, offering new avenues to probe the quantum nature of space-time. She earned her BS from Bethel University in 2001 and PhD from University of Washington in 2006, followed by postdoctoral positions at Fermilab and University of Wisconsin. Before joining Caltech in 2019, she was on the faculty at the University of Michigan. Her accolades include being named a Simons Investigator, a Fellow of the American Physical Society, and receiving the Seaborg Nobel Travel Award. Let us welcome Professor Jurek and request her to start her inspirational talk for all of us.
Okay, well, thank you very much for the kind introduction and for the invitation to speak to you. And good morning, good evening from California. And I'm going to talk about the intersection of gravity with quantum, in particular in observables and interferometers. And so what I'm going to talk about, in contrast to the previous talk, is still very much in the realm of ideas, with the development of an experiment using quantum technologies that I'll talk about at the end. So it's not established for many years now, like the previous distinguished speaker. What I want to talk about is the idea that we could measure the quantum effects of gravity in interferometers. And to do that, I want to introduce some ideas. And the first idea that I want to talk about is the idea that when you make a measurement in a laboratory, what you're doing is to create a horizon. And so that's what I've shown here. So this is based on some work in 2019 that I did with Eric Verlinde. And what I'm showing here in the center is the two arms of an interferometer. So here's a beam splitter at the center of this picture. And then there are two interferometer arms that radiate out to some far mirrors, shown here as blue and red patches. And on the right, I have represented this in a space-time diagram where time flows upwards. So here's the beam splitter mirror, and here's a far mirror. And what happens in an interferometer is that you bounce light in between the beam splitter and the far mirror. And in these diagrams, light travels at 45 degrees. And so this diagram is called a causal diamond. So what it does is it tells you that there's a region of space-time that's being measured by your apparatus and a region of space-time outside of your apparatus that isn't being measured. So you can think of experiments again as measuring causal horizons. And so the question that we asked was quite simple. We wanted to know, what are the quantum effects of gravity in such a measurement? So the other talks that you're going to hear about gravitational waves are about the classical effects of gravity, but we wanted to ask about the quantum effects of gravity. So I would imagine that most of you are familiar with the measurements of an interferometer, such as for gravitational waves that measure ripples in space-time. And those can be either due to classical or quantum effects. So if there's a gravitational wave propagating from a far source, that is that would be a classical effect. And I want to talk about the ripples in space-time that would be due to quantum effects. And it's important to keep in mind what these incredible experiments, gravitational wave experiments, can actually measure. Because what they do, in fact, is to measure space-time fluctuations that are on the order of 1 part in 10 to the 20. So that's what's shown here. So if you look at this plot here, it shows what's called a characteristic strain as a function of the frequency. And you can see that an experiment like LIGO, at least back of the envelope, would be sensitive to a fractional fluctuation of 1 part in 10 to the 20. It's incredible. And it turns out that if you turn this size length fluctuation into numbers, what that corresponds to is a length scale, which is the geometric mean of the Planck length. And I'll tell you in a minute what is the Planck length as a number, and the size of the interferometer arm. So in the case of an experiment like LIGO, this is kilometer scale. Now, you don't hear people talking about quantum effects of gravity in interferometers, and there's a good reason for that. The reason is that the traditional view is that quantum gravity effects are only visible at ultra short distances. So when we talk about quantum gravity, we expect that the space-time, which is represented here by the blue blobs, will fluctuate. But the typical length and time scales that we expect it to fluctuate on are something like 10 to the minus 35 meters. And not even an exquisitely sensitive interferometer like LIGO or Virgo or Kagra would be sensitive to those very, very small length scales. And even the future interferometers wouldn't be sensitive to these length scales. And there's a good theoretical reason why we, in the past, have always believed this to be the case. And the reason is that, that when you do an effective field theory expansion, quantum gravity appears to be perfectly well behaved. And any corrections to the gravitational potential appear at higher powers in G Newton. So they're actually corrected by this very short length scale, the L Planck squared scale. And those are just far too small to be observable in this picture. And this is the reason, one of the dominant reasons why both theoretically and experimentally, we've never gone after quantum signatures of gravity. However, what I want to spend some time talking about today is that increasingly, we're realizing that this picture of gravity and its quantization may in fact be naive, that there can be non-local effects that appear in the presence of horizons. And one context in which this has been very well studied is in the context of black hole horizons. So it's quite well known that black holes have an entropy, and the entropy of a black hole is the area of its horizon. This is the Gibbons-Hawking entropy. And entropy is information. It counts the number of bits. So, so if I think about this from a quantum information theoretic perspective, the entropy is the area in units of the Planck length. So if I were going to visualize this in terms of bits, if we're going to visualize a black hole horizon in terms of bits, I could think about it just schematically as having this many number of bits that are then free to fluctuate. And so what we say is that black holes are holographic. And you might say at this point, well, wait a minute, I thought you were talking about measurements in gravitational wave interferometers in some Earth laboratory where there is no black hole. Why am I talking about black hole horizons? And the reason why I'm talking about it is that it's known that black hole horizons are not so different in some cases from these causal diamond horizons that I talked about on the first slide. In fact, there are some cases where there's in fact an exact dictionary between a black hole horizon and a causal diamond horizon. And in fact, it can be shown exactly, and this is a little bit of technical jargon, for something that's called a Ryu-Takeyanagi diamond that appears in the context of ADS-CFT. And the horizon now on the causal diamond is the horizon that's defined by light that you send out in an interferometer. The analog of the black hole temperature is the size of the causal diamond, and so forth. All of these quantities, including the entropy, has an analog for this empty causal diamond. Now, why is that interesting for measurements that you make with an interferometer in a laboratory? And we get a hint of that with some work that has been done in the context of black hole horizons, where these degrees of freedom, the pixels, are able to fluctuate thermodynamically. So the idea is that you have these pixels, you have an area on 4G worth of these pixels. There are many of them. They have a temperature that's set by the size of the black hole horizon. They're allowed to fluctuate. And then what happens is that causes the mass of the black hole to fluctuate, and that shifts the horizon. And when you do that calculation, what has been found in different contexts is that the position of the horizon shifts by an amount that depends not just on the Planck length, but also on the size of the black hole horizon. So when I say an infrared scale enters, that's what I mean, is that there appears not to just be a Planckian effect, but there's also an IR effect. Now, this is not known to be observable. And in fact, it's still a question of debate to what degree precisely black hole horizons are like laboratory, the horizons that are created when you make measurements with light in the laboratory. So what we've set out to do is to explore to what extent are light sheet horizons, the horizons that are created in interferometers, just like black hole horizons, and in what sense precisely is that true? So what we'd like to know is, what is the quantum theory of gravity, which in this context means we want to know what are the quantum operators. In other words, what are the analog of X and P? And what are their quantum commutators? And the interesting thing is that we've been able to work out that the relevant degrees of freedom that respect general covariance is an area operator, very similar to black hole horizon, and something that is a time shift operator, called here alpha. And we found that this commutator, rather than being proportional to h bar, actually just goes like G Newton. So this is a result of a technical paper that I'm going to tell you a little bit about. But we've been able to piece together this picture from a variety of different standpoints. And we believe that it's related to the way that the vacuum of quantum gravity sheds soft gravitons. And I'm not going to have time to go into those details, but I just want to give you a little flavor of how it is that you go about quantizing the causal diamond in flat space. And I'll talk a little bit about the procedure just to give you an idea that there are real calculations that back up this idea that when you create a causal diamond in a laboratory, when you create a horizon, that horizon has properties in common with black hole horizons. So to do this, to quantize this causal diamond at light sheets, what we wanted to do was to understand the Hamiltonian dynamics and the phase space. So in quantum mechanics, you work out the phase space. You find, in this case, we work from the Einstein-Hilbert action. We don't want to break the symmetries of general relativity, so we don't want to break general covariance. But we do want to construct the Hamiltonian consistent with the symmetries of general relativity and whatever are the conserved charges. And this is a method that was worked out largely by Bob Wald and his collaborators. Once you've done this, just working from the Einstein-Hilbert action, you're able to read off what are the symplectic pairs, which is to say you get the operators that allow you to construct the Poisson brackets. So this is the analog of X and P in quantum mechanics. Then you quantize by promoting those Poisson brackets to commutators. So in the interest of time, because I have very little of it, I'm just going to skip over the details of how we do this and just tell you what the result is, that after we did some work in this computation, we find that the symplectic potential and pair depends on the area that bounds this interferometer. And now I show this area here as a sphere. And you can ask me the question, what is the relevance of a sphere bounding this interferometer where I'm sending light out from the beam splitter? And the answer to that is that it is the set of points that's equidistant from the origin. That's the relevance of the sphere. And the other degree of freedom that's relevant is a time coordinate. Okay, so it works out to be something that's a time coordinate that here is called u. And the symplectic pair is just mu wedge the area. So what happens then when you promote this, you can then invert it to get the Poisson bracket, and from the bracket you can promote these to quantum commutators. And you find not only this bracket, but you also find the Hamiltonian charges. There are two of them, one associated with each of the degrees of freedom entering into the commutator. And interestingly, one of those Hamiltonian charges is proportional to the area. And in fact, we find that it satisfies thermodynamic relations that were actually predicted by Ted Jacobson. And furthermore, the other of these operators actually seems to cause these causal diamonds to nest. So the way that I think about this is in terms of a Russian doll analogy. So when I send a photon out from a beam splitter, what happens is the region of space-time evolves as and it becomes larger until it reaches the final, until it reaches the far mirror, and then it evolves back into the beam splitter mirror. And so one thing you can ask is what happens to observables as the photon evolves through this series of nested causal diamonds? Well, we don't fully know the answer to that yet, but one hypothesis that is consistent with the data is that as the space-time evolves through the series of nested causal diamonds, that each nested diamond has an uncertainty associated with it, which is on the Planck scale. And if this quantum uncertainty that comes from this underlying quantum commutator is a noise in space-time, which is to say it's statistically uncorrelated, and if it's allowed to accumulate, which happens if there's a gravitational memory, we expect there to be accumulation of uncertainty. And so you can calculate what is the accumulation in position uncertainty from evolving through this series of statistically uncorrelated nested causal diamonds. And the answer that comes out of doing that exercise is that the accumulated uncertainty is just this geometric mean of the size of the interferometer arm and the Planck length that appeared previously in the context of a black hole horizon. So that's interesting. I'll skip over this in the interest of time. And so if this scaling that I've worked out for you in a very parametric way holds up to further scrutiny, it might suggest that there could be a quantum uncertainty in space-time that not just depends on this extremely small length scale, the Planck length, but also depends on the size of the interferometer. So, which is to say the size of the region of space-time that's being measured by your apparatus. Now, at the moment, there are many things about this theoretical framework that we have understood, but at the moment, these calculations estimate the size of the effect, but they leave out some crucial observational effects. Notably, we haven't yet computed from first principles what's known as the power spectral density. So that is to say the amplitude of these fluctuations as a function of the frequency. And this is complicated by the signal being dependent on the apparatus itself. So depending on whether you're making the measurement in a relatively large experiment like LIGO or Virgo, or a space-based experiment like LISA, or in PTAs, the amplitude of the signal is actually expected to be different. That's one of these signals. And so as a result, we really need to make detailed experiment-dependent predictions for what might be observed. And so what we decided to do in collaboration with my colleagues at Caltech was to build a model and then make detailed experimental predictions based on that model, with the goal eventually of being able to derive the true model from first principles. So if I can make an analog, it's like when you first study quantum mechanics, you learn about the Bohr atom of the hydrogen, but the Bohr model of the hydrogen atom, but you don't yet have the full theory that describes the hydrogen atom in full. For that, you need the full Schrodinger equation. So this is a model that is meant to mock up some of the aspects of this signal without yet having all of the details of the theory. And so this model was called the pixelon. And the reason why it's called the pixelon is because these bits, the area worth of bits, now are modeled as quantum degrees of freedom that cause the celestial sphere here to fluctuate. It's a breathing mode. And the way that it's modeled is through the density of states of this degree of freedom called the pixelon. And the density of states, which is here written as sigma, is just given by the square root of the entanglement entropy, which is just the square root of AN4G, which this equation is inverted. It should look like L Planck on L. So you can make this calculation, and one thing that people often ask me is, well, why is it that you don't see this signal in LIGO, which has extremely good sensitivity to small length fluctuations? And the reason for that is fundamentally because LIGO is a Fabry-Perot instrument that recycles the light. And what that means practically is that their sensitivity to a signal as a function of the frequency is actually peaked at frequencies that are well below the light crossing time in the interferometer. Whereas we expect this signal from space-time noise to actually be peaked somewhere around the light crossing time. Okay, and this is two models for the infrared cutoff, okay, of the theory. And so what we've done is to design an experiment that focuses with a similar sensitivity as LIGO to this region where you have just the single light crossing time. And this experiment, as it's being implemented at Caltech, is called GQuest, Gravity from the Quantum Entanglement of Space-Time. And it was designed by my colleague Lee McCullough. And one of the things that makes GQuest unique, and I want to point you to this figure that is taken from these two papers, is that in contrast to the interferometers that exist today, where you send light out to two mirrors and then you look for the shift in phase, the relative phase between the light and the two arms, Lee had a different idea to look for gravitational waves. His idea was that if a graviton interacts with a photon in this laser, it will actually scatter the photon. So then what he wants to do is to have a series of cavities that filter out the laser light and just look for the single photon that has been scattered by the gravitational wave, whether that's classically or from this quantum effect of gravity. And then he wants to detect that single photon with a device that's called an SNSPD. These are often used in quantum computing to look for single photons. And so the idea here is that the signal for a kind of 5 to 10 meter apparatus is peaked in the 10 megahertz range. So the idea would be to look for photons in sidebands that have been scattered from the laser into either sideband. And this is an experiment that is being developed. So I'm going to go ahead and conclude. And I just also wanted to say that you can make predictions for future interferometers. And I think eventually, if this space-time noise due to quantum gravity exists, it will be detected. We have a theoretical collaboration that's ongoing, exploring aspects of of how we look for signatures of quantum gravity, whether in interferometers or other kinds of setups. People have different sets of interests. So let me just conclude by saying that it's not hopeless that we could observe signatures of quantum gravity in Earth-based interferometers. And the thing that allows us to get around this no-go theorem of local quantum field theory is that when you have horizons, non-local effects become important. And that ends up meaning that the infrared scale can become important for observables in laboratories. And it is possible that in the future that noise due to quantum fluctuations of the vacuum of quantum gravity could appear in future interferometers. So thank you.
Thank you very much, ma'am. Whenever we say that actually the quantum science is the language of nature, the presentations and the inspirational talks like yours and Professor Jain actually verifies that yes, it is. That the era has gone when experiments were done, and those experiments were understood in terms of a particular modeling or theory. Now the era uh, is uh, in your leadership, in the leadership of the theoreticians who are actually paving the path for the generation or the invention of new technologies for the well-being of uh, mankind. Uh, thank you very much again, ma'am, from all of us, the organizers and the participants. And
Thank you.
now we welcome the next speaker, who is the director of the Raman Research Institute. Professor Tarun Choradeep, sir. Sir, good morning and welcome, sir.
Okay.
Sir, am I audible to you, sir?
Yeah. Just 1 minute.
Sir is there. He has already connected, and I think
I need to rejoin. Can you hear me?
yes, sir. Yes, sir.
Oh, okay, great.
If you want to, if it is needed, you can rejoin. Otherwise, you are audible, sir.
No, okay, fine. I thought I wasn't audible, so
No,
that's okay.
So welcome, sir, and thank you very much, sir, for inspiring to make this subtle effort of ours in a big way, so that the young generation could listen and understand what is the impact of quantum science on the present day technologies. So our inspiration for holding this conference is Professor Dr. Tarun Soradeep, who is the present director of Raman Research Institute, Bangalore. I think all of you know the Raman Research Institute, which was established by Professor C.V. Raman, the Nobel laureate from India. It was his inspiration that now the seat is being taken over by Professor Tarun Soradeep. He this role he has held since January 2022. An internationally acclaimed physicist, Professor Soradeep has made pioneering contributions to cosmology and gravitational wave physics, helping place India at the forefront of these global scientific endeavors. Beginning his academic journey in mechanical engineering at IIT Kanpur, he transitioned to cosmology, earning his PhD from Inter-University Center for Astronomy and Astrophysics, IUCAA, Pune, and later completing postdoctoral work at Canadian Institute for Theoretical Astrophysics. He has held key academic positions at IUCAA and served as professor and chair of the physics department at IISER Pune. Professor Swaradeep led India's only participation in the European Space Agency's Planck mission, significantly contributing to cosmic microwave background research. He also played a crucial role in establishing India's presence in gravitational wave astronomy, including leadership in the LIGO India project, a major international collaboration approved by the Indian government in 2023. His research addresses fundamental questions about the early universe and challenges to the standard cosmological model. Among his many honors are the Kruber Cosmology Prize, Special Breakthrough Prize in Fundamental Physics, DST Swarn Jayanti Fellowship and fellowships from premier Indian science academies, and many more to come. So let us welcome Professor Swaradeep and listen him carefully.
Okay,
Sir.
thank you so much. And I'm really glad that, this year you're able to organize it. So let me first share my organize this symposium for the benefit of students. And I think that's very important because India is making, efforts to get into major scientific enterprise, and it's very important.
Sir, just for, I think you know, but Director National Quantum Mission, JBV Reddy sir is also there, and Professor Janendra Jain sir, your good friend, he is also, although it is very late there, but he is also listening to you, sir.
Okay, I'm sorry, there was a glitch and I had, the Zoom sort of exited. So I'm back. Let's see how things go. Is my screen visible to everyone?
Yes, sir.
Okay, great. Okay, so again, thank you very much for the invitation, and I must congratulate Yogesh and his colleagues for, kind of making this event really annual affair that I'm sure the student community, and particularly ones in Jaipur and around, are really cherishing. And this is also an amazingly important occasion because it's the first end of the first decade since the milestone discovery of gravitational waves. I would say not discovery, but it was detection of gravitational waves. We already knew that gravitational waves must exist, but it was an indirect detection, inference. But what happened on 14th September is something that is still, quite etched in everyone's minds. And at the risk of being repetitive, let me replay the video that LIGO Scientific Collaboration created to say what this event was. So now, as I tell students, this is like, one should realize, if you're not in astronomy or cosmology in particular, the scales are huge, right? So what we are talking about happened in a galaxy far, far away. So it's actually, light takes a billion years from there to come here. And but if you were in the galaxy and looked up at what is the Milky Way, or the galaxy itself, the stars in the galaxy, if your Earth was present there, and you looked carefully with very high resolution, optical telescope, you would see that this Milky Way was like what it is on the sides, but you would see that um, at two places it was pockmarked by two black shadows. Now, this shadow is also something that another effort from radio astronomy and millimeter wave astronomy, which is Event Horizon Telescope, has also shed light on. These are like, shadows of the black holes. So there are two black holes in these faraway galaxies, and they, if gravitational masses, get attracted, and if they have any angular momentum, they will coalesce after orbiting each other. So this is what happened, and I'll just pause it here to tell you that this is really a new window to understand space-time. And, I should also mention that although we have been very successful in physics, there are two very successful strands of um, physics that are yet to come together, which is quantum science and theory of gravitation. So anytime we, probe on either side very, very hard beyond what we have probed before, it's important to keep doing that till we uncover how these two are related, because there are very basic conundrums that would, that are difficult to understand, where you want to kind of make quantum science consistent with, the theory of gravitation. So that is the motivation for us to look for extreme events where the space-time is really churned up. So what this video clearly shows you, and I like this video for that reason, is this distribution of stars in the background, which are, obviously moving around because of the gravitational lensing. And they basically also indicate the amount of churning of space-time that's happening near black holes and two merging black holes. So you can see the two merging black holes merge into one, and there's this little shiver you will see now, okay, and settles down into another much bigger black hole, right? So now that's one reason you should be studying that. And this event, has been such events happening all the time, but humankind could first detect this event in a new messenger, the gravitational waves, and these come at the speed of light, and we received this signal on 14 September 2015. Okay, so at one go, it was basically heralded as the discovery century because it was a hat trick. So you first detected gravitational waves directly with a man-made apparatus. This was also the direct detection of a black hole, maybe not statistically so, but at least there was a clear thing that something like a ring down happened. So what formed at the end seemed to be a black hole, and that in subsequent detections, a lot more, has been shown much more clearly in other events. Okay, and from the astrophysics point of view, this was the first time we knew that black holes exist in binary systems. Okay, now, it's of course, if they are black holes, then binary systems is not surprising. But the point is, black holes are the end state of stars, and the stellar evolution ends many times with a pretty explosive event. And it is always a issue of how do you make sure that two black holes which are bound together remain bound past the this the explosion. Okay. I also wanted to mention that since I'm giving the Indian perspective, India has been sort of associated with this. So Professor C.V. Vishweshwara, who was in Maryland as a student of Charles Misner, and either at the end of his PhD, early postdoc, he first showed that black holes ring, and there's a very pure tone, so which basically can completely allow you to pin down the mass of the black hole, and other just another parameters is rotation. Okay. And in India, since the 90s, there have been two groups. So at Ayuka, Professor Durandar and P. Satyaprakash, um, who they started laying the foundations of data analysis. So they did quite a number of work, which were quite useful start to this whole area. I mean, match filtering. And then in Raman Research Institute, where I am, Professor Bala Iyer had led a group together with some French collaborators and did really seminal work on foundations of source modeling. What is the kind of signal you expect from merger of black holes? So the signal that you expect is already, in that overlay. You can see that. Yeah. So you can see that the black hole merger, happens here. And, this signal is something that you need to be able to predict so that you can pull it out of the very noisy data. Okay. So now why are these systems? And we have seen many, many such systems. So at this point, I think the LIGO scientific collaboration has seen 200 plus 230 years or compact binary mergers in gravitational waves. And so this was the first part of the fourth observing run, 048. This is recently, the catalogs, and you would have seen these pictures. Now, why are these so important, and why, again, for quantum physics, they're important? Okay, so now imagine that you want to understand the structure of a particle. So, for example, when we wanted to understand whether protons are made up of further subdivisions, which we know, now quarks and things. So, what have particle physicists been doing? They have been taking protons and smashing them into each other at almost the speed of light. This happens every day, billions of times in the Large Hadron Collider. Now, of course, for space-time, we can't build any apparatus on Earth, so we have to seek these events happening somewhere and hope to observe them. This is the game in cosmology. So all the talks that you'll hear, you'll see cosmology or astrophysics. We don't have necessarily a lab in which we can recreate anything, but you have to see physics happening. So you have to have the ability to observe physics happening at the extremes. So this is extreme because you see you have a black hole of the mass of 30 solar masses and a 40 solar mass in this first event, which got together and merged to give something like a final black hole of 67 solar masses. Now, what I wanted to point out is you look at the relative velocity of these black holes before they merged, and you can see the relative velocity exceeded half the speed of light. Okay, now that is something extraordinary, right? You have something with the mass of 30 solar masses and 40 solar mass, crashing into each other almost at the speed of light. Now, if anything were to be discovered in the structure of black holes or, then this is the kind of phenomena you want to model and understand very well. Okay, so this has a lot of bearing on the kind of talks you heard earlier, like do we have, effects that need to be understood in both space-time and quantum as they try to come together. Okay, now also, as I said, physics at the extreme. So in this particular event, 3 solar mass got converted into gravitational waves in 0.2 seconds. So the luminosity was huge. If you look at the thing, it's 10 to the 49 watts. And, it was brighter than all the stars in the universe for that period. So all I want to say is when I want to go beyond the frontier. So I have quests which I have to, first solve. So when we, managed to detect gravitational wave, that was a conquest of a quest. But now we have more quests coming up because there are things that we are seeing which we need to understand. Okay, now I wanted to emphasize also to the audience in the context of India why, I have been sort of so keen that we start, building or be part of building, frontier apparatuses. Science is always discovered, using the frontier apparatus. So again, if I'm in Raman Research Institute, so Raman effect, Raman had seen that effect, or he had guessed that there was an effect, not guessed, but he had very good visual and audio faculties, so he could see some hint of light. But ultimately, to win the Nobel Prize, he had to get a spectrograph of the best of that time, and then prove what he was seeing. So similarly, if I want to see these effects which are tiny, the gravitational waves, the space-time is stiff. So even if such an energetic event happens, all that happens is two mirrors placed 4 kilometers away, move by about attometers, right? And we need to be able to do that. So this is where, this is the story that is always happening. So there are things that we have in our daily experience, but physicists have been moving into, scales that you can't see, but we are, doing atomic physics and nano, then nuclear physics at femto. But now to this kind of science, we have to breach this attometer, you know, uh, sort of boundary of being able to probe science on those small scales. Okay. And that is quite interesting. Of course, this discovery was immediately recognized with a Nobel Prize because, as I said, I mean, it's difficult to argue against the fact that this was certainly the discovery of the century, and it is kind of something that will stay with us for centuries ahead. And just on the side, I mean, what really happened with the fact that we were at that time committed to build a LIGO India detector since 2011, group of us got together, made a consortium, and we committed to build the third LIGO in India. And then that also meant that there was a science team involved and many others involved from 9 Indian institutions. So I think it was an excitement that has kind of spread to others that there was some participation in this scientific milestone discovery from India. This is kind of not happened in a long time. So it was kind of looked at as a big. Now, to detect these things, you have to, build frontier apparatuses. Not all apparatuses need to be big, but in this particular case, the apparatus that you have to use is a, Fabry-Perot-Michelson, Fabry-Perot enhanced Michelson interferometer, and that is not on the tabletop of your labs. I mean, I think many students who have been in physics labs would have seen a Michelson interferometer. But this is at 4 kilometers, right? So it's not only science, but it also needed technology barriers to be breached, right? And this is the whole story. So one of the reasons that US pursued this program over 4 decades was because they realized that this is going to open up, breach the boundaries of technology on many fronts. Okay. And so these are pictures from LIGO Hanford, just showing you the scale of the apparatus. So you can see there's a person standing here on this thing. I don't know whether you can see the cursor. but you can just see the scale of things happening. And what is exciting is something like this is now going to come up in our country, and the kind of things you have to do technically are such that this definitely people getting involved in this would be valuable across the board for many experiments, even for other experiments like the previous speaker talked about, very exciting experiments. What one wants to see is, once you have such a enterprise happening in the country, it opens the door for students to take up challenging areas of science and then grow into looking at other frontiers. But the ability has to come by first setting a baseline which is high enough and comparable to the frontier. So this is a picture of it's a 3D rendering of the drawings, engineering drawings of LIGO India. I can't guarantee it would look exactly so green. It's fairly dry place, but otherwise it's actually two specs. And this is the central hall, and then there are two arms stretching out 4 kilometers. And as I said, we got an approval, in principle approval in 2016, full budget approval in 2023, April 7th. Site was acquired way back in 2019-20, and we are into construction phase. And there are 4 lead institutes involved in this enterprise. Now, why did we want to build a LIGO? It was explicitly stated. We never, even in 2011, when there was no detection, we never have a line in our proposal which says we will participate in the detection. Because my sense was that, it would be within few years of advanced LIGO that we will make detections. So this was something that I could sort of got convinced in 2009 or something, when there was this document saying what advanced LIGO would do. But then the question was, 2 LIGOs by themselves cannot locate a source on the sky. So for the first discovery, the gray part shows you the uncertainty. And actually you can fit 7 Big Dippers in this area. So it is Big Dipper is this constellation called Saptarishi. It's a huge constellation. Now you can fit 7 of them. So now if you ask an astronomer, okay, go search for something happening in that area, and you will have one of the leading astronomers speaking to you right soon, I guess. And then Mansi Kasriwal, and she would tell you this can be done. So what they would like us to do is to locate the origin of the gravitational waves to a much smaller ellipse. And LIGO India allows that by a huge factor. And this science case, although this is what we presented way back in 2016, in fact, to the Prime Minister, this picture was made by Varun Bhalera and Leo Singer, and to show how important this thing will be. And besides the science, which was to enable the launch of gravitational astronomy, of course, from the Indian perspective, it would bring in high-end frontier technology, which I already mentioned. I also wanted to mention another thing which is not often mentioned. We have strategic geographical advantage because we'll be separated by 12,000 kilometers from the US one. But that's not all. There are many countries which are separated from US by that kind of distance. I felt that India stands out uniquely because of our demographic advantage. We are a youth-dominated country, and it's almost imperative for us to provide challenges to the young people. And this kind of an enterprise, I must mention, because a lot of students ask me, what do I need to get into LIGO enterprise? I think LIGO India probably should be open to almost all branches of science and technology. So if you are an engineer, you can get involved as an engineer. You can be a data science person, get involved. You can be, of course, one of the, very deep theorist, or you can be a very good, someone making very precision instruments. So that kind of a broad spread. So what really we envisaged is LIGO India would connect to all these areas, so of astronomy, fundamental science, precision, and all the technologies. So all of these getting pushed as we talk, okay, with LIGO India coming up. Okay, so let me just give you a little bit of the status. So the status is that, way back in 2016 itself, we had concluded a 5-year effort to, narrow down potential sites for LIGO India. You can see these triangles, and we finally, homed in on this site, and so Ondha is a tiny town, almost a hamlet in the middle of the Deccan Plateau. And, I think in 2030, it would be, kind of known worldwide as the detector comes online. Okay, what is interesting is geologically, we have found a really good site because it's right in the middle of the Deccan Plateau, and the seismic characteristics have turned out to be good. And we have, these are pictures from very early times when we were, exploring various things. This other thing, the truck is basically the trucks which do geotechnical evaluation and things like that. At this point, one building I'm aware of is ready, but you will have talks from people in the LIGO team who I'm sure will show you much more recent pictures. But this is also an all-weather station that has been working there for a long time. So what are the challenges ahead? One challenge is to get the Indian industry to build this mammoth structure, right? I mean, to me, every time I look at it, I get very, challenged in the sense that look at the size. It's 4 kilometers, 8 kilometers, plus these areas of contiguous vacuum held in these beam tubes and these chambers. And about 10 million liters of space is held under ultra high vacuum. So to achieve this, we needed to ensure that our industry can do this. So we took the essential elements of this and made sure that industries could build that. So this was done in the period between 2018 to 2020, and the Indian industry did successfully produce these chambers. You can see the size of these chambers, and they are quite a bit challenging because they had to do things which are a bit unconventional, but they managed to do that. And we are really happy to do that, see that. And then we managed to transport it on the Indian roads, which you would realize is not such a given thing as in many other countries. So it went from Bangalore, where it was fabricated, to Indore. And then here is a picture, I mean, again dated, of beam tube section being prototyped, and then that beam tube section now with all the baking coils around it, baking wrap around it, and a cryo pump, which you can't see here. It's on the bottom of this. All in place at Institute for Plasma Research, and they have all the control systems, and they have been able to pump this down to the required vacuum uh, levels required. And this cryo pump, I should mention, was built by one of the industries in India, and not a very big one. So, the capabilities exist in India, which are definitely going to make it possible to build the exterior thing. And I'm sure soon a big company is going to, be awarded the whole work. And then you have the task of setting up all this fairly complex optical uh, apparatus within those chambers. And so to that end, we have a national testing and training facility at RRCAT, which was built with a large hall where a 10-meter prototype is being built. So now let me, do I have a few minutes more? I don't know how long I've taken. Dr. Chandra? Dr. Chandra, can you hear me? Okay, so I just wanted to spend a little time saying, so LIGO India is on the way to construction, and this will open up a new kind of science and technology ecosystem, as well as as also kind of managed to kind of excite new aspirations. So the next goal in gravitational waves, which if you listen to Ray Wise's Nobel lecture, is gravitational waves from cosmic birth. So that's something that we are now focused on. So we are, we have a proposal that India participates or leads a satellite which will detect uh, gravitational waves of cosmic origin. And the way to do that is quite amazing. So in LIGO, you have mirrors which are placed 4 kilometers away, and you look for the distortion in that configuration. Now, what nature has provided us is a plasma screen, which is placed 43 billion light years away. So this gigaparsec translates to about 43 billion light years. And now if you look at that plasma screen and you have a gravitational wave going through it, it gets distorted. I mean, this is of course exaggerated. And these distortions can be detected in the cosmic microwave background polarization field as these world patterns. And that's something that we can, the community is gearing up to do that. So this is a proposal, again, a consortium, just like Indigo was set up. We have a consortium called CMB Bharat, which is pursuing this. And the basic idea is a modest, not modest, somewhat mid-sized space satellite, which will travel to L2 and do these measurements. And again, this requires, what it requires is to breach the ability of power measurement. And we know that our cell phones, actually you may not know, that can detect picowatts of power. And here we have detectors which can measure attowatts of power. And even then we have to pack thousands of them to make this detection. So this is a typical focal plane. And this is not something that is, in the future. Such focal planes are already on telescopes in the Antarctic and, Chile, trying to look for these signals. But space is the best platform for such an enterprise. And, um, I mean, there are other things which I don't want to get into, but I just wanted to say that to me, the LIGO India effort has, from Indigo Consortium, has sort of gone to do this thing where we have a major, I think probably the largest pure science project underway in India. And, I'm sure that already there's a huge community, but I'm sure this will grow into a major uh, enterprise in the country. But then my next thing is what next? So this is something that I would envisage happening in 2040s, where we would have the ability to work with the best space agencies and scientists across the globe to produce something that would detect the gravitational waves from the beginning of the universe. Thank you so much. Hello, can you hear me?
Yes, sir.
Yeah.
Okay.
Thank you so much. I'm YK Vijay from Jaipur, colleague of Dr. Yogesh Chand Sharma. Probably he's not answering right now. So it's a great effort, sir. Thank you so much for sharing all those details for our young participants who are connected with this event. There are more than 106 participants participating in
wow.
this event all over India and abroad. And well, maybe it's a technological marvel, I can say, when it comes to, and certainly we want to be different than others in India. So the uniqueness you have mentioned in this event is that we are connected with the Vedas, earlier studies, and the location which you have chosen is really a remarkable effort. And we are working at both fronts, from outer space, the microwave background detection and its monitoring, and also at the ground. So it's a remarkable effort for Indian people to join this mission with you, and I congratulate you to take a lead at this time.
Thank you so much,
Thank you so much
Dr. Yogesh.
for
And I
sharing.
again want to reiterate that I am really happy that this effort is being taken
Sure.
to spread the word to students. And that's
Yes.
vital, because one of the things that's very important is all the efforts. I can see Dr. Reddy up there. So there's a national science mission going on, quantum science mission, and there are, and this LIGO I didn't mention, but I'm hoping Suresh or someone will mention this, has very deep connections to quantum metrology. So in some sense, it is almost like a part of the National Quantum Science Mission. And, some of the things that was mentioned by my previous speaker are the next kind of quantum tricks that we may be using. And this is not my thing. I have a very good colleague, Rana Adhikari. He keeps telling me that, there are a
I
lot
mean,
more
both
things
the
that would be
speakers have
possible.
really
So I think
justified.
this is amazing for students to be able to listen to all these great guys. And also, I'm really thankful that so many people are, from all over the world have agreed to speak at this. So I congratulate you on
Thank
that.
you, sir.
Thank you, sir.
Actually, this effort which is coming up in India, it is very inspiring for the young students, because it will be the real science on the ground, and we are able to participate in the international level of frontier areas of science through the people like you. So thank you very much again for
Thank you
being
again.
with
Thank
us
you very
and
much.
address. Uh, I request you to be with us, sir. Now I request our honorable Vice Chancellor, sir, Professor Victor Gambhir, sir, to address the gathering and welcome you all. Professor Victor Gambhir holds a bachelor and master's degree in mechanical engineering from reputed institutions like Thapar Institute of Engineering and Technology, Patiala, Punjab Engineering College, Chandigarh, respectively, and PhD in Quality in Engineering Education. He has 41 years of experience with 4 years in industry and 37 years in education. He is presently President and Vice Chancellor of JECRC University, Jaipur. He has worked as Vice Chancellor of his SGT University, Gurugram, Vice Chancellor of Maharishi Markandeshwar University, Maulana, and Pro Vice Chancellor and Director Planning and Manav Rachna International Institute of Studies and Research, Deemed University at Faridabad. A Joint Director, Technical Education Department, Government of Haryana. He was very much instrumental in executing 2 World Bank projects for development of technical education in Haryana, as head State Project Implementation Unit and Technical Education Quality Improvement Program for technical educational institutions in Haryana. At a cumulative cost of 260 crores, he was heading the Secretariat of Government, Haryana Government State Fees and Admission Committee. His research area include institutional ranking, accreditation, and quality of education. He has published and co-authored many textbooks, and in journals. He has been awarded 2 patents. He is a member of American Society of Mechanical Engineers, senior member of American Society of Quality, fellow member of Institution of Engineers, past president of Haryana State Chapter, and life member of Indian Society for Technical Education. Professor Gambhir's leadership has elevated the standards of learning and research at JECRC, making it one of the most sought after universities in the North India. I welcome Professor Gambhir, sir, and request him to address the gathering.
Thanks, Yugaji. Thank you very much. I'm audible.
Yes, sir, you are audible, sir.
So, thanks a lot. It is a proud privilege to extend very warm welcome to Professor Janinder Jain from Penn State University, US, who was chief guest of this online international conference on quantum science and technologies. And he delivered his lecture in the beginning of this ceremony. I also extend very warm welcome to Professor JBV Reddy, Director, Quantum Science Mission, Professor Tarun Soradeep, Director, Raman Research Institute, who highlighted the quantum sciences and technology in a very apt manner. I understand that he is one of the illustrated scientists from India with H-index of 106 and more than 1 lakh citations. So it was a great privilege for the participant to hear from him on such a relevant topic. It is my, again, privilege to extend warm welcome to all the participants who are participating, not only from India, but from abroad as well. United Nations has declared 2025 as International Year of Quantum Science and Technologies to celebrate the quantum mechanics, which happened almost 100 years ago. And we have established a center of excellence of quantum science and technologies in the university recently. And Professor Yogesh Sharma is heading that center of excellence as director. He had planned this international conference while he was with other university, and we had a very short notice to organize this conference on this JECRC platform. So it is I thank Professor Yogesh Sharma to manage this or organizing this international conference on such a small notice, and that's why it is predominantly being done online. The future of quantum sciences and technologies promises to be transformative, and we are now moving from theoretical research to real life applications. I'm not a subject matter expert, but I understand that the future of drug discovery, AI-enabled quantum technologies, and then areas like cryptography. There are so many areas where we will be able to do very major applications, industrial application and real-life applications using quantum technology, qubits, quantum computing, again, is thing which is being talked about. And with the patronage from Professor JBV Reddy, Quantum Science Mission Director, and Professor Tarun Soradeep, I think we will be also able to contribute a bit in this direction. And once again, I thank all honorable and esteemed guests and all the participants. Thanks. Thank you very much. Namaskar.
Thank you very much, sir, for your kind blessings. And now we have with us Honorable the Mission Director of National Quantum Mission, Professor JBV Reddy. Sir, am I audible to you?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
So, just a minute. Professor Dr. JBV Reddy is the Mission Director, National Quantum Mission, Scientist F and Head, Quantum Technology Cell, Department of Science and Technology, Ministry of Science and Technology, Government of India, New Delhi. He is senior scientist and key government official leading India's efforts in emerging quantum technologies. As the mission director of the National Quantum Mission and scientist staff and head of the Quantum Technology Cell at the Department of Science and Technology, Ministry of Science and Technology, Government of India, he is the forefront at implementing India's initiative on quantum mission launched in 2023 to establish global leadership in quantum science and technologies. Dr. Reddy holds degree in Electronics and Communication Engineering from Delhi College of Engineering, an MS by Research in Power Systems Engineering from IIT Delhi, and a PhD in Advanced Signal Processing and Machine Intelligence from SOE University, Bhubaneswar. With over 3 decades at DST, he has played a significant role in national and international R&D programs. Under his leadership, the NQM aims to develop quantum computers with 50 to 100,000 physical qubits, satellite-based secure quantum communication, and 2,000 km of intercity quantum key distribution. He also champions the development of human resources, collaborating with the AICT to launch UG and PG programs and lab infrastructure. Before focusing on quantum technologies, Dr. Reddy contributed to DST's clean energy initiatives, including smart grids, energy efficient buildings, and clean coal technologies. His work reflects a commitment to fostering indigenous innovation and building to robust quantum ecosystem for India's future. Sir, we welcome you and request you to address the gathering online and offline, both.
Thank you very much, sir. I am sharing my PPT.
Sir.
May I share my PPT,
Yeah,
sir?
yes, sir. You can share.
Share. There is an option here. Share. Oh, yeah, it's there.
Yeah, it is there.
I hope are you able to see my screen, sir? All
Yes,
of you?
it is coming, sir. Now you can. It is there, sir.
Yes, yes. Oh, it is okay. Moving also. Yes, right?
Yes, sir. Yes, it is.
Thank you very much, sir. Thank you very much.
Sir.
Professor Victor Gambhir Saab, Professor Tarun Saab, Professor Jurek Saab, and Professor Jitendra Kumar Jain Saab, and Professor P.K. Ahluwalia Saab, and Sharma Saab, and all the participants of International Conference of Quantum Science and Gravitational Waves. With a warm greetings from the Department of Science and Technology on behalf of National Quantum Mission. Quantum technology is one of the 9 missions of the national importance. This mission is being driven by the Prime Minister's Science Technology Innovation Advisory Council. This mission intends to leverage cutting-edge scientific research. Department of Science and Technology is implementing this mission along with the key ministries like DRDO, DOS, DAE, MIT, and DOT. Quantum technologies have critical application potential across several vectors. For example, in communication sector, it can improve the data security. In health sector, it can enable less invasive and more accurate diagnostics and considerably increase the speed of drug discovery. In finance sector, it can enhance the security of the transactions and increase the speed of big data analysis and much more. NQM has 4 verticals: quantum computing, quantum communication, sensing and metrology, materials and devices. These are some of the technology domains. NQM has specific deliverables in all 4 verticals.
Audio तो हो रहे हैं.
Video नहीं जा रहे sir. It is not. Are you able to see my screen? Slides move हो रहे?
Yes.
Yes, sir. Yes, sir. It is.
Okay. Some cross-talk came. That is the reason. Sorry. For example, in quantum computing, target has been set to develop quantum computers with 1,000 qubits. In quantum communication, target has been set to develop secure communication, both satellite and fiber-based networks. In quantum sensing and metrology, target has been set to develop magnetometers, gravimeters, and atomic clocks. And in quantum materials and devices, target has been set to develop new materials and devices for all these 3 verticals. NQM has a structured roadmap which will be implemented in 3 phases. In phase 1, focusing on prototype development. In phase 2, product development and deployment. In phase 3, business development and economic growth. Department of Science and Technology has established 4 thematic hubs, and these T-hubs will coordinate with the technical groups, and these T-hubs will create the innovation in the quantum science and technology. These T-hubs are the Section 8 companies. These T-hubs are responsible for technology development, capacity building, and startup support, and industry partnership, and international collaborations. I would like to apprise you about the thematic hubs and technical groups. Quantum Computing Hub established at IISc Bengaluru and coordinating with the 4 technical groups. Communication Hub established at IIT Madras in association with the CDOT, coordinating with the 5 technical groups. Sensing and Metrology Hub established at IIT Bombay, coordinating with the 2 technical groups. And Materials and Devices Hub established at IIT Delhi, coordinating with the 3 technical groups. And launched on September 30th, September 2024. You can see from the launching ceremony. And these T-hubs are brought in about 150 researchers from 43 institutions across India. This is a pan-India program. And DST would like to facilitate the growth of startup ecosystem and make them active part of technology delivery. And T-hubs will create the national facilities and open to the startups, and also will provide technology and business mentoring and equity support. NQM has developed exclusive guidelines for effectively onboarding the startups, since it is in nascent stage and requires huge investment, and supported 8 startups in phase 1 and launched on 26 November 2024. DST intends to actively engage the industry stakeholders to enable technology transition. Through T-hubs, industry will have access to the national facilities and co-develop the technologies and eventually develop a revenue sharing model. As a part of the NQM, Department of Science and Technology initiated Quantum Awareness Program among the students, researchers, industry professionals, and policymakers. Through this initiative, DST intends to build capacity and contribute to policy development. As a part of this initiative, NQM, in collaboration with AICTE, developed a curriculum on quantum technologies for BTech minor and MTech, launched on 24th December 2024 and 28th August 2025, respectively. And efforts are underway: book writing, recording of video lectures, and faculty development programs. Department of Science and Technology will support the technical institutions for setting up the laboratories in quantum technologies. And also, in addition to this, rolling call for supporting startups in quantum technology is open, and any startup can submit the proposal in all 4 verticals, all 4 T-hubs. Thank you. Thank you very much. Over to you, sir.
Thank you very much, sir, for letting us know what actually quantum mission is driving. And it is what is needed for the young students to participate. Thank you very much, sir. I thank to you, but Professor Swaradi, our Honorable Vice Chancellor, sir, and other dignitaries who are there to bless this particular event. Now I will request Professor K.S. Sharma, sir, who is the President of IUPT Rajasthan chapter, to deliver vote of thanks and his blessings also.
Thank you, Professor Sharma.
Sir, I think your video is not audible.
Yeah.
So,
video is probably not working, so
I will share your photo, sir.
Okay, sir.
So that will be, so that everyone knows. सर का नहीं है उसमें? अच्छा सर, आप एक बार कंटिन्यू करिए।
Yes, sir.
हाँ।
Honorable Dr. J.V.V. Reddy, Mission Director, Quantum Mission, National Quantum Mission, Professor Victor Gambhir, Director, JECRC University, Bull Prize winner, Ivanpur University Professor, Jainendra Kumar Ji Jain, Professor Catherine M. Jurek, Professor Tarun Souradeep, Professor Edward Harhi, Professor Y.K. Vijay, Professor Yogesh Chandra Sharma, and other dignitaries present in this meeting, in this conference, and participants. It's my pleasure to give vote of thanks for this prestigious event. First of all, I thank Professor Y.C. Sharma for conceptualizing and organizing this international conference on quantum science ICQS 2025, funded by National Research Foundation, and along with also organizing the fourth seminar on the discovery and detection of the gravitational waves. The Professor Sharma has organized previous three such conferences on this discovery and detection of the gravitational waves, which are creditable for him, as this type of events have been organized by him only in Rajasthan. The credit for direct observation and gravitational waves goes to LIGO Observatory, who were able to directly detect these waves in 2015 after 100 years of their prediction by Albert Einstein in 1916. The importance of this conference can be further realized in the wake of the Indian government initiative for setting up of the National Quantum Mission and establishment of the LIGO Indian Observatory, and the role of quantum phenomena in the upcoming quantum computing, and declaration of the year 2025 by UNESCO as the year of quantum science and technology. On behalf of the organizers, I express my sincere thanks to the speakers of today, Professor Jainendra Kumar Jain, the Wolf Prize winner of 2025 from Penn State University, USA. Professor Jain hails from it's a matter of pride for us that Professor Jain hails from Rajasthan and particularly from Samar Lake. So it's a matter of pleasure for us that one of us is at such a high position and he has won the Bull Prize. I think he is an aspirant for getting Nobel Prize in coming few years. Professor Catherine M. Jurek, California Institute of Technology, Professor Tarun Souradeep, Director Raman Research Institute, Bangalore, Dr. J.B.B. Reddy, Director National Mission of Quantum Science, who have given their valuable inputs in this inaugural session, which have set the roadmap for the conference. Professor Jain has spoken on unification of the integral and fractional quantum Hall effects with the help of the composite fermions. Professor Jurek on infrared effect of the quantum gravity and interferometers and black holes causal diamond. Professor Souradeep on black holes black holes, gravity waves, and quantum science. Twin black hole, a beautiful explanation with pictures was given for twin black holes merging together and gravity waves. And also about the Indian contribution to the same and in the LIGO project. Professor Reddy, Dr. Reddy, Director National Quantum Mission, has enlightened us about the activities which Department of Science and Technology is doing and the infrastructure developed in different parts of the India for furtherance of the science and technology in India to that high level contribution. Also, I extend my thanks to the speakers of other sessions, Professor M. Kasliwal, California Institute of Technology, Professor Edward Harhi, Principal Scientist, Google, Professor Yogendra Narayan Srivastav, Northeastern University, Boston, Dr. Varun Raghunathan, IISc Bangalore, Professor P.C. Deshmukh, Vice President of Indian Association of Physics Teachers, Professor Arunava Mukherjee, Shah Institute of Nuclear Science, Mr. Hitesh Kumar Golati, Scientific Officer G, associated with the LIGO project, Indian Observatory Mission, Professor Manjari Bagchi, Institute of Mathematical Sciences, Chennai, Professor Suresh Deravari, IUCACAA Pune, Professor Manish Rimali, Central University of Rajasthan, Dr. Sugam Kumar, IUAC Bangalore, Dr. Patrick Dr. Dr. Patrick Das Gupta, New Delhi, Dr. Venugopal Acharwa, Director NPL, who have very kindly accepted our request to become part of this event and give their valuable inputs. Further, I thank all the participants who, who took part in the quiz competition, and particularly those who have been declared winners of this competition. More than 500 participants have registered for this conference. I welcome and congratulate all of them. Their participation is important for making this event a success. The Center for Excellence in Quantum Science and Technology, JECRC University, MNIT Jaipur, BIT Mesra Jaipur campus, Indian Association of Physics Teachers, Regional Council 6, Rajasthan, and Material Research Society of India, Rajasthan chapter deserve special thanks for collaborating to organize this international conference. I would put on record my appreciation to Professor Y.C. Sharma for making it possible to associate renowned scientists and researchers and teachers from all over the world with this event. I am sure that this will make a great impact on every participant and will open windows for further research in these areas. I also thank JECRC University for hosting this event and providing the Zoom platform for this online international conference, and other institutions and organizations in collaborating and giving strength to the host. I am sure all the sessions are going to be quite interesting for all the audience, and they will be certainly benefited by the new knowledge which they will get from nicely chosen galaxy of speakers by Dr. Sharma. I also thank media persons and realize the importance of this international conference and to give it a proper coverage in newspapers, TV channels, and also on social media. I also thank all the volunteers and the IT personnels involved in management of this conference. In the end, I again thank all the speakers, all the participants, JCRC University, and other institutions, organizations collaborating in this event, and in particular, Professor Y.C. Sharma for his untiring efforts to give this event a big dimensions. Thank you very much.
Thanks. Thank you. Thank you.
Thank you very much, sir. All of you, sir, for your blessings. I'm sorry that due to technical glitch, Professor Sharma cannot open his video. Sorry, sir, we could not see you live, but we can listen, and your vibes were truly reaching to us. So thank you very much all. And since we are into the session 1 now, straightforward, and Professor Mansi Kasliwal is already with us. Ma'am, can you hear me?
Yes, can you hear me?
Ma'am, you can open your video and audio both. Thank you very much, ma'am. It is so late, but still you are there to inspire the young generation of India with us. Professor Kasliwal is Professor of Astronomy at Caltech, USA. She is an Indian-American astrophysicist and Professor of Astronomy at the Caltech, Known for her pioneering work in transient and multi-messenger astronomy. Her research focuses on discovering and understanding short-lived cosmic events, cosmic fireworks, such as supernova, neutron star mergers, and electromagnetic counterparts to gravitational waves, which shed light on origin of heavy elements and stellar evolution. After leaving India at an age of 15 to pursue science in US, she earned her BS in engineering physics from Cornell University and a PhD in astronomy from Caltech in 2011. She held postdoctoral fellowship at Carnegie Observatories and Princeton University, returning to Caltech as faculty in 2015 and earning tenure in 2021. Professor Kasliwal's group specializes in robotic wide field sky surveys using optical and infrared cameras at Palomar Observatory. She discovered a new class of stellar explosions, gap transients, and leads the Growth Project, an international telescope network that tracks fast evolving celestial events around the clock. Her team plays a key role in gravitational wave follow-up, rapidly identifying light from mergers detected by LIGO. She has received the New Horizons in Physics Prize, Packard Fellowship, and a Fellow of American Physical Society, among other honors. Her innovative work continues to shape the future of time domain and multi-messenger astrophysics. Ma'am, welcome, and I request you to start with your presentation.
Are you able to see my screen?
Yeah.
Can you hear me okay?
You're able to see your screen.
Okay. So thank you very much, Professor.
We can hear.
Thank you very much, Professor Sharma, for this opportunity to talk to all of you and share a little bit of my excitement for multi-messenger astrophysics with you today. I grew up in Indore in India, and I love to come back to India every year. And now, thanks to the Webber Fellowship of the Department of Science and Technology, I'm able to visit every summer and build on the collaborations I have with India scientifically, and it's a great honor and privilege to do that. So what you see here on the screen is in one of my favorite cosmic fireworks. So I study flashes of light. So things in the universe don't stay the same; they're continuously changing. So if you follow with me now, what you will see here, you see two neutron stars spiraling towards each other, emitting lots of gravitational waves, a really loud gravitational wave signal. And then they merge to form a black hole. They launch a jet in the gamma rays. The jet launches a cocoon that lights up optical, infrared, and ultraviolet emission, and then eventually a very long-lived radio emission. So what you're seeing in here is the essence of multi-messenger astrophysics, where you have gravitational waves as well as photons, electromagnetic waves from the same source. And this opens an entirely new window into studying our beautiful universe. So this is what I will tell you more about today. Before I say anything else, I have to share that the biggest perk and privilege of being a professor at Caltech is the opportunity to mentor really amazing students and postdoctoral fellows. And many of them are from India. Many of them are now returning to their home countries as faculty. And it gives me great pride and joy to work with these people. And I will credit their contributions throughout this talk. I also have the privilege of leading the growth collaboration. So by its nature, when we're looking for flashes of light and we are seeing them fade, then it's amazing that if you have a group of friends around the world, you can actually beat sunrise. So let me explain what I mean by that. So let's say we're at Palomar Observatory, which is where I have most of my discovery engines. We discover a new flash of light. One star became brighter than the sun by a factor of 1 billion. Now this star starts to fade, right? And it starts to become fainter and fainter every hour. So you can study it from Palomar Observatory, but only for a few hours before the sun rises. Because to study optical and infrared astronomy, you actually need it to be nighttime. So how do you now continue to study the source when it is fading so quickly? The idea is you just keep moving in the longitudinal direction so that you can continue to stay in the dark skies and continue to collect data from around the world. So from California, you go to Hawaii, then you go to Japan, Taiwan, India, Israel, Sweden. So you follow this whole network of telescopes around the world, and you keep passing the baton as you would in a relay race for telescopes to collect data. And this makes it really helpful and essential to actually have a global partnership to study the changing skies. Now, all of this is in the backdrop of the physics messengers, which have in the last decade. So I joined Caltech exactly 10 years ago. And 2 weeks after I joined Caltech was the event that Professor Tarun Saurdeep described to you so eloquently just a few minutes ago. This was the discovery of gravitational waves from the merger of two very massive black holes. Now, since then, we have more than 100 black holes that have merged with each other. There's an entire field of black hole astrophysics that it has opened up, and the Nobel Prize has been awarded for this work. I'm going to tell you about the piece of black holes that neutron stars can actually do better than black holes. Just in case people aren't familiar with what is a neutron star, so neutron stars, the name suggests, is a very, very densely packed ball of neutrons and other particles. Think about something the mass of the sun packed in just 11 kilometers. So it's extremely, extremely dense. It's 10 to the 15 grams per in each 1 centimeter by 1 centimeter cube. And neutron stars are formed when a massive star ends its life. When a massive star ends its life, the outer layers get thrown out, and the inner layers collapse to form this very dense neutron star. So now when you have neutron stars that are merging instead of black holes that are merging, you have the opportunity to study this not just in gravitational waves, but across the entire electromagnetic spectrum. And here I show you a beautiful collage of just telescopes with increasing sensitivity at every wavelength, right? Everything from the highest energy gamma rays to the lowest energy, longest wavelength radio waves. And all of these are essential because what they do is they illuminate gravitational waves. So this is the same concept as let there be light, right? I mean, so when two black holes merge, you don't necessarily get associated with it photons that you can study. So now I'm going to give you this one example, which is by far the most beautiful moment and life-changing moment for me, which was on August 17th, 2017 at 12:41:04 UTC. There was this amazing 100-second long signal that was very, very loud. It was the loudest thing that the gravitational wave interferometers had heard to date. And you can see what they've the detection in this chirp that is here. So you can see it was detected by LIGO Hanford and LIGO Livingston, but the Italian interferometer actually didn't really see it. But the fact that it didn't see it actually contributed very, very critically to the science because it helped understand where in the sky the signal was coming from. And what really opened up the astronomy side of gravitational wave astronomy here was that about 1.7 seconds later, after this gravitational wave signal, there was a burst of emission seen in the gamma rays by both the Fermi satellite and the integral satellite. So this meant that there were photons that were coming from the same place as those gravitational waves. Now, these are the highest energy particles, but like gravitational waves, they're no good at telling us, exactly where the event happened. So when you first look at it, right, there are these big areas of the sky that it could have happened in. As you start to localize things better, say, oh, Virgo didn't see it, that's why it has to be here in one of the null spots of Virgo. You can localize it to some number of galaxies. But what you end up needing is an optical or an infrared telescope to tell you, no, this galaxy right here and in this exact position of this galaxy, this is the true home of the transient. So this is where information from different pieces of the electromagnetic spectrum come together, and you can study this one source. Once you found out exactly where it happened, right? And now you know things to not 100 square degrees, but you now know things to like a pencil beam position of less than an arc second on the sky. Then every telescope in the world for this particular event, what you see here is that every telescope in the world, about 70 telescopes, 70 telescopes worldwide, and 7 telescopes in space, dropped everything they were doing, whatever data what they were planning to collect. They stopped collecting that data, and instead they pointed their telescopes to look at this particular neutron star merger that had given birth to a black hole and launched a jet of some sort. So to study this and to collect data from this, there was this completely unprecedented campaign using all the telescopes in the world to look at this one point in the sky where something absolutely spectacular that we had never seen before had happened. And this led to many, many, many papers, right? I mean, it was the cover of Nature, Science, Astrophysical Journal, everything, right? There was so many papers of about 3,000 astronomers working on this. And many fun things were learned. And I'm going to give you just 2 examples of what fundamental questions this one firework could answer. So the first question that I'm sure everyone in the audience, all the students in the audience must have thought of at some point is what are you and I made up of? Where are all of these building blocks of life, the elements that you and I are made up of? You mug up what is in a periodic table. There are all these elements. But where are these elements actually made? Because if you go back and think about the history of the universe and the Big Bang, it was mostly just hydrogen and helium. That came from Big Bang nucleosynthesis. And most of the universe is very simple. But if you look around us, you look at what you are made up of, or I'm made up of, or the things we use are made up of. We're made up of all types of elements in the periodic table. We use materials which involve all types of things in the periodic table, but we don't know where half the elements in the periodic table, heavier than iron, are actually made. So this was the fundamental question that we made immense progress on, right? So we had known hydrogen and helium comes from Big Bang nucleosynthesis. Thanks to telescopes like the Zwicky Transient Facility at Palomar Observatory and others, we now know of over 10,000 supernovae. So we know where all the things in light blue and dark blue are made up of. They're made in supernovae. But the things in yellow, we were seeing for the very, very first time. And this is half the elements in the periodic table, heavier than iron. So all of these elements are made in a process which is called our process nucleosynthesis. It's the rapid capture of free neutrons so that you can make these heavy nuclei without getting beta decay, where the neutron just breaks up into proton and electron. You're overcoming all the repulsive things by those neutrons and neutrons and protons don't want to stick together in a nucleus. So this happens in a very extreme environment, which is when a black hole is born from the merger of 2 neutron stars. And how do we know that we were actually seeing this? It is thanks to all that data from the 77 telescopes that I was telling you about. So now if you take the data from the 77 telescopes, all these astronomers and all these, you can see all the references here, and you just say, okay, something became very bright and then it started fading. So what you're seeing on the y-axis is brightness, x-axis is time. So something became fainter as a function of time. It also became very, very red as a function of time. And nothing could that we had previously seen could become so red so quickly. So what is so interesting about things being very bright and blue at early time, but then being very, very red at late time? And here the connection is to actually look at the elements that are being synthesized. If you make a very big element, then it has lots of neutrons and protons in the nucleus, but it also has all these energy levels that are filled out by the electrons, right? So remember, going back to your high school chemistry class, you start filling out not only the S shell, the P shell, but also the D shell, the F shell. And if you have so many possible places for electrons to live, imagine a photon that's making its way to you from this black hole that was born to the Earth, to your telescope. This photon can get absorbed and re-emitted by any of those electrons. So what astronomers call this process of distraction, because of the large number of energy levels in heavy atoms, is opacity. So the opacity is so high that the peak of the emission very quickly goes from hot and blue to very red. And that's what you see in the sort of sequence of spectroscopic data that was the movie that just played. But by far, we had the most vivid evidence that no matter how you analyze this data or which group analyzes it, what theories you use, this was the most direct, most compelling evidence that we were seeing the formation of heavy elements, elements heavier than iron in the periodic table for the very first time. So this was our process nucleosynthesis in action for the very first time. And then sort of the more detailed questions are, so which of the heavy elements were formed? What were their relative ratios? Can it explain all the heavy elements that we see on planet Earth, in the solar neighborhood, et cetera, right? And one of the things that fascinated people the most about this element, about this heavy element nucleosynthesis, was that if you go all the way down to now, number 195 and 197 on the table, that's gold and platinum, right? So even the heaviest of the heavy elements, right, going through the lanthanides, the actinides, the really heavy elements, which give you the reddest emission. There was data from which I'm showing here, which is from the Spitzer Space Telescope, one of NASA's 4 great observatories. It was tantalizing hints, but that even the heaviest of the heavy elements were formed in this particular neutron star merger. So in fact, the elements I circle in red are the heaviest elements that were probably formed in the most amount of quantity. And we were really starting to make progress in understanding the origin of elements in the universe. So that is sort of one big thematic question that we made a lot of progress understanding. Another question is, so what happened to that black hole that launched a jet, right? And what happened to those gamma rays that happened just 2 seconds later? And are these neutron star mergers things that we have known since now the 60s, called flashes of gamma ray emission, very high energy emission, called gamma ray bursts? So are these two things related or not? That was the second big question this could answer. And it turned out that actually this was a very difficult question. It was not a simple yes or no question. Because what the gamma rays that were actually seen in this event, it was a very short 2-second duration, but it was actually a very weak emission. So compared to a normal gamma ray burst, of which now again there are several hundred to thousands known if you look past in the last few decades, the brightness or the intrinsic luminosity of this gamma ray burst was a factor of 10,000. I'm not just saying 1% or 2%. I'm saying a factor of 10,000 times weaker. And when we're looking at a jet, we're usually looking at things when you're looking down the barrel of the jet, right? You're looking directly down. And in this case, why was it so weak? So, the first thought that came to people's mind is that, maybe in this case, you were not looking at the jet directly, but you were looking slightly off axis. So you missed most of the jet, but you're looking slightly off axis. Maybe that's why it appeared to be weaker, but actually it's the same thing. But the problem was the story just didn't hold, because it seemed to get a factor of 10,000 weaker, you would have to be very off axis. So we very quickly knew that this was not the right answer. It was just not consistent in what you were seeing in the gamma rays versus what you were seeing in the radio, right? In the two extremes of the spectrum. In fact, there was no radio emission detected for the first 9 days. It took a very long time to see radio emission. So this was not a very simple, straightforward connection to gamma ray bursts to explain the jet physics. So the gamma ray burst was weaker by a factor of 10,000, and the radio and the X-rays stayed hidden for nearly 9 days. So what we decided to do is try to just take all the data and put it together in a concordant picture and say, what are the energetics here? What are the kinematics here? What could be happening that is different to give you a weaker event? And so what you see here is the cocoon model. So imagine these two neutron stars that are spiraling around each other. They're ripping off so much material from each other. It's called tidal disruption. That the surrounding in which this jet is launched is very, very messy. There's a lot of material there. So when this jet gets launched, it actually gets stuck. It's not easy for the jet to break out of the star because of all the neutron star material before the merger. So what this jet ends up doing is it transfers its energy to the surrounding material. So instead of a very narrow, very collimated jet that you saw in this previous picture, right, you end up getting a very wide angle jet. So you're transferring the material over a very wide angle. So instead of something going at 0.99999 times the speed of light, you end up getting something that's going only at about 0.99 times the speed of light, right? So this is the difference between the Lorentz factor of 100 and say a Lorentz factor of 10. So Lorentz factor is 1 over square root of 1 minus v square over c square. So this makes a very, very big difference. We call this mildly relativistic instead of ultra relativistic. And the small difference is actually the key to explaining what we saw. It can explain why the gamma ray emission is weaker because you transferred the energy. You're now not as relativistic as you were before. And it also explains why it takes some time for this cocoon to break out and to actually give you radio emission and X-ray emission. So it solves those two puzzles very, very nicely. And it turns out, maybe eventually the jet did break out somewhere. So if you had a friend on an alien civilization that was aligned in the direction of the jet, someone somewhere saw a regular gamma ray burst. But what we saw was on Earth here was the breakout of a cocoon. So that was, we had a lot of fun. And now there are, even today, there are papers still being written about this event from 8 years ago. There are at least 3,000 papers in the literature explaining this one source alone and the various facets of physics. I just gave you two questions that it definitely made a huge progress in answering. And since then, I know the question is, have we been able to find more of these events? And here I go back to what Professor Tarun Sordeep was telling you about earlier this morning. The challenge here is to find more and more such events is that you have to map very large areas. LIGO Hanford and LIGO Louisiana and Virgo cannot do it alone. The only way to solve this problem is you need very good on-sky maps. And you need something like LIGO India to really come in and play a role in breaking these very, very large maps into more smaller areas so that we can start to find things. Even with these larger areas of thousands of square degrees, we map these large areas, we find all kinds of transients that are coincident with it. We look on all different time scales. We use lots of telescopes to try to characterize them. But it's very, very difficult, right? We use a lot of actually machine learning and software infrastructure that is state of the art to tackle this problem when you're trying to deal with these very large area localizations. But it's very, very hard to find associated electromagnetic emission. To do this right, you really need another gravitational wave interferometer that is and India is in the perfect geographical location for this, that can take those thousands of square degree maps and convert it to tens of square degrees, right? It can make at least 2 orders of magnitude difference in the size of the sky that you have to search. So that this problem goes from being an annulus to like actually just the center of the annulus to just a handful of tiles that you can then focus on and then pinpoint, here's the transient. This is the one that's actually related. That said, one of the newest mysteries that's keeping me up at night recently is that when we saw the gravitational wave event from August 17th, 2017, it was two 1.4 solar mass neutron stars that were merging. Just one month ago, on not even 1 month yet, on August 18th, 2025, there's this very interesting signal. It was sub-threshold, But there was this very interesting signal from LIGO Virgo Kagra collaboration, which suggested that maybe you can form neutron stars that are less than a solar mass. This is fundamentally not allowed if you think about the Chandrasekhar mass limit that Professor Subramanian Chandrasekhar came up with many decades ago. So how do you even form neutron stars that are smaller than a solar mass? And if you form them, could you actually see a transient? So this is a transient that we discovered at Palomar Observatory, which is very unusual. It's inside this tiny little galaxy at a very far off distance of 400 megaparsec. And we are currently exploring the association between the signal and the formation of these subsolar neutron stars. So this could be an entirely new chapter in multi-messenger astrophysics. We don't know yet, but we are exploring this very actively. And my team is losing a lot of sleep in trying to understand this event right now. It's only been 3 weeks. Let me now move on to another thing that we had no idea could exist, right? So far Professor Saurdeep told you about 2 black holes merging. I told you so far only about 2 neutron stars merging. Now, what if you had 1 neutron star and 1 black hole? Is it even possible for them to be in a binary system? Do such things exist in nature? Can they merge? And until 2019, we had no idea that this could actually happen. They were completely a figment of theorists' imagination. But in 2019, the gravitational wave interferometers started uncovering neutron star black hole mergers, not once, not twice, but many times now, more than a dozen times now. There have been compelling neutron star black hole merger candidates. So far, none of them have yielded an electromagnetic transient, a light associated with these neutron star black hole mergers. So one is forced to wonder, are these neutron stars being swallowed whole by the black hole? Like, is that entire neutron star just falling into the black hole? And maybe sometimes it happens, especially if the black hole is much bigger than the neutron star, then it could happen a lot. But if the black hole is small and the neutron star is small, you could actually get a very bright red source. And this source would be even redder than for binary neutron star merger, even more luminous in the infrared bands than the binary neutron star merger. And it would become redder even faster because you're forming so much of those heavy, very heavy of the heavy elements, the heaviest of the heavy elements here. So this forced me to think about, okay, maybe if you want to find light from not just binary neutron star mergers, but if you want to find light from neutron star black hole mergers, we need to build some new tools, some new telescopes. Because in the optical, we have some very sensitive, very wide field telescopes, but we don't have that in the infrared. So I've been experimenting with new technologies, in particular with using indium gallium arsenide instead of mercury cadmium telluride and putting up some detectors at Palomar Observatory called Winter. And I'm very happy that's actually working. This is a beautiful camera here on this Winter telescope at Palomar. And this was actually a student from IIT Bombay who came into the PhD with me and is now starting a Hubble Fellowship, whose thesis project was the Winter telescope. This is Viraj Karambilkar's project. And what this is leading to is building an entirely new wide field infrared system. And this, when combined with a new high energy system that my host for the Webb Fellowship, Professor Varun Bhalerao at IIT Bombay is doing, can give you some really new new ways to look at the universe, can open up our eyes into entirely new ways. So Professor Bhalerao is working on a mission called Daksha, which he wants to build and launch entirely from India, that can tell us something that we can't even, we're just starting to see hints of right now, right? In terms of gamma ray bursts, long, short, which ones give kilonovae, which ones give these multi-messenger sources, which ones don't. It can really open that up. And in the infrared, based on some of these early results from these new detectors that I've been using, there's a path forward to build a dream machine in the infrared, And because the sky is so bright in the infrared almost everywhere on Earth, we actually need to go to a very cold, very dark place called the Concordia Plateau, Dome C, in Antarctica. And if this project is successful, and we have a 1/5 scale prototype that we are going to take to Antarctica next year, if this project is successful, it will be just as even more sensitive than Rubin Observatory in the Y band, and 5 times more sensitive than the Roman Space Telescope. And it's all because of very, very innovative optical thermal design. And there's some hardware here that is the only thing that can give us this ability that is otherwise completely limited by how bright our sky is and how cold you need to be to actually get past that. So I'd like to wrap up here by just expressing my by the sheer excitement of the kinds of telescopes that are coming online now in the decade looking forward, that have orders of magnitude higher survey speed. And survey speed is the metric for discovery here. It's how quickly can you image the sky? How deep can you go? So what is the volume you're actually probing per unit time, right? So when you're making a movie of the sky, you want to make a movie of the sky as fast as possible by building something that can go deep and wide and repeat fast, right? So this volumetric survey speed is sort of the discovery metric. And Daksha will play a really great role in this on the highest energy ends. But all of this has to be backed up by software. So you can't do it with hardware alone. So you need software that can integrate the different LIGO India and LIGO Hanford, localizing things to this point, then going and imaging it, taking those large number of data, things that change in the night sky to saying this is the one that is truly physically associated, coordinating between the 77 telescopes worldwide. You need a lot of machine learning, a lot of software tools, which is another area where India actually really shines, is this software interface. And of course, the third and most important component to discovery, and all these three things have a multiplicative effect on discovery, in addition to hardware and software, is grayware, right? And grayware is basically just brilliant minds, right? The people that are actually working on this and are dedicated to understanding and uncovering the mysteries of the universe together. So discovery potential is literally the product of hardware, cutting edge new hardware, very robust, very innovative software, and brilliant minds. So I'd like to conclude by saying that we're in a very exciting era of multi-messenger astrophysics, where we are looking at an entirely new window of the universe. We're talking about, we don't know whether something existed or not, and seeing things that we've never seen before. Quite literally, without exaggeration, those statements are true, right? I mean, it really is a revolution in time domain discovery right now. And India can play a forefront world-leading role in this, because number one, with LIGO India, if you can figure out where something happened, then all the telescopes can actually point and combine light and gravitational waves, not just one time, right, but over and over and over again. And not only for binary neutron stars, but also for these subsolar neutron stars, also for neutron star black hole mergers and things I can't even imagine right now. That ability is extremely powerful and unique to what LIGO India can do. The second, I think, Daksha, as I've mentioned a few times now, would be very powerful in the high energies. And India, I mean, just more generally, I mean, and I'm, more and more convinced of this every time I go. I mean, the people talent in India is very powerful. So the grayware is actually a core strength, and just with the right training and the right, it can really go places, because you can multiply hardware, software, and grayware in India in a way that the discovery potential will have. Sky will not be the limit. So with that, I'd like to thank you for your time and attention. And if anybody has any questions, I'm happy to take that as well.
Thank you very much, ma'am. I think it is very late. Still, we are troubling you and many other speakers. Professor Farhi, he could not join us because he was there with us in the morning. But since it is very late, so he said, I will speak at a later time, whenever it will be possible for him. Also, one of the speakers, Professor Yogendra Narayan Srivastav, he will be speaking, I think, at 11:50 or so. So let us thanks Ma'am Kasliwal for providing us a glimpse of what they are doing and how she is trying to connect what they are doing at US with the people who are at India. Ma'am, if you can think, we request you to be with us at Jaipur for the next visit. You were there at IIT Bombay when we last got connected, but now you please plan your next visit to Jaipur because it needs to be spreaded. Uh, there must be many pockets working. Good. We are also trying to understand how we can contribute. So your visit will enhance our moral boost and will provide us a scientific direction in which we and our students can contribute and participate.
I would love to. It would be a pleasure, my pleasure and honor to visit Jaipur next time.
Yeah, thank you, ma'am. Thank you very much. So we will have a short break, and I think after this break, whenever Professor Yogendra Narayan Srivastava will be able to join us, we will start. Thank you, ma'am. Again, thank you very much.
Thank you. Good night.
Bye, bye, ma'am. Bye, bye. Good night, ma'am. So I will start my presentation on how it is important that we should learn quantum science. So am I audible now, sir? Am I audible? Audio is there, no? But the screen is.
Yogesh, you are very much audible.
Sir, just a minute, sir. Actually, this screen is not visible properly, I think. इसमें properly नहीं हो रहा ना screen share?
Screen, we are able to see a frozen pen.
Yes, sir.
So it is not moving. Otherwise, it is visible.
It is not moving. I should see that. I should share it again, sir. Now it is moving us. So let me start with my talk on whispers of quantum universe, materials that speak the language of space. So I thank our Honorable Vice Chancellor, sir, for motivating me and providing the logistic support which was needed to organizing this particular event at a very short notice. Thank you, sir, for believing in what we are trying to do. So my talk will be having the movement like this, that I will introduce the quantum mechanics briefly, how this quantum mechanical theory is able to predict not only about the topological materials, but uh, other things also. So theory comes before experiment. It is what the phenomena is nowadays. Although it started a very long ago, when Einstein predicted that there must be an entity like gravitational waves in 1916, which was found in 2015 at the LIGO laboratory, USA. Similar kind of laboratory is being developed at India also. And then we will delve upon to how these topological materials are important for today's technology and how these materials are contributing in space, how they are providing the power, heat, and the quantum technologies which are needed for the satellites and GPS technology and other quantum technologies which are the present day need. And I will end up my talk with how we should strive for educating the quantum revolution to the students, and how we can create and chart the quantum future for the space and beyond. Participants and friends, quantum mechanics was developed in just 2 years. The main contribution came from Heisenberg and Schrodinger, and the work is still going on to develop a perfect theory. But as Feynman said, we are still trying to understand this theory. So why quantum theory was developed? It was because the schizophrenic behavior of light, which was observed initially as particle type by Newton, then ultimately it was proved as a wave-like phenomena by Maxwell, although theoretically, but experiments also proved that this is a wave-like phenomenon. There were other experiments like Michelson's experiment and photoelectric effect, for which Einstein and Michelson both got Nobel Prizes. They were not fitting into the human understanding during the last decades of 19th century. Also, the basic element of matter named as atom was thought to have positive and negative charges, such that the positive nucleus was thought to hold the negative charged electrons so that to produce a stable structure. But the classical theory was not able to understand how it was a stable phenomenon. According to classical theory, this must collapse and the positively charged center should uh, eat up the negatively charged particles and vanish. So to messing up the things more, there was one famous experiment by Young. Most of you have studied it in your 10th and 11th and 12th classes during the initial introduction with the physics. In this experiment, not only light was behaving as the wave, but later on when the experiment was done with the electrons also got interfered and similar kind of fringes appeared. So a wave particle duality appeared, including the formal formal double slit experiment, which was done by Thomas Young for light only. But then the electron diffraction also proved that electrons are also behaving as waves. They were thought to be confined in a particular space and behave like particles. But in this particular experimental results, they were also behaving as wave. To fit these observations, based on the wave particle duality concept, Schrodinger developed his famous or derived his famous equation named as Schrodinger equation. This also we studied during our first introduction with the quantum mechanics, either at BTech first semester or second semester engineering physics level, or in the BSc or MSc quantum mechanics classes. This equation assumed that the particles are actually stationary waves in their energy levels, and that is how they are simultaneously moving as well as are confined in the space. This was not easily digestible because the fundamental property, the wave function, was assumed to be connected with the probability of the finding of the particle. Although Schrodinger developed this equation and tried to find out a modeling, but the wave function which was connected to probability always puzzled. And people, the stalwarts like including Einstein and others, they were not able to digest it. But the results of the Schrodinger equation in terms of free electron theory of metals and quantum tunneling, they were perfectly in connection with the experimental results. We can say that the free electron theory of metals provides us the number of free electrons available for metals almost perfectly for copper and other perfectly conducting materials. Similarly, the tunneling in which it is assumed that an alpha particle exists and it strikes the wall of the nucleus for 21 times per second, but it can take up to 10 to the power 11 years to come out from a particular nucleus. So earlier to this, for the 10-20 years, it was not explainable how radioactivity can happen. But for the first time, quantum theory provided an explanation of these two phenomena, remarkable matching with theoretical results, the experimental results of metals, and the perfect explanation of radioactivity were the first concrete evidences that quantum mechanics is the language of the nature. Our mother nature speaks in terms of this particular mathematical language. Although this language is counterintuitive, human understanding or human senses are not trained or not provided strength to understand things like how the quantum mechanics speaks. So we are struggling, we are still struggling to resolve the concept of wave particle duality and may have hurdles to accept it still, how these particles and waves can behave in a synchronized way. But once we are able to find out the solutions of this particular problem, I think we will be able to produce more applications of quantum mechanics, and our technologies will be better than what they are today. So this was the introductory thing which I wanted to share with you all. Thank you very much for patience hearing. And I think the next speaker, Professor Yogendra Narayan, he will be speaking from Rome. So if he will be ready, then we will connect him. Otherwise, at 12:30, Dr. Varun Raghunathan from Indian Institute of Sciences will be with us. So we can have a break of around 30 minutes or so. We'll again join at, I think at 11:50. So it is only 10-15 minutes break. So those who can remain joined, please remain with us. Otherwise, you may have some break for some time, and then we will connect at 11:50. सर है ना वहां पर योगी श्रीवास्तव सर इज देयर है ना योगी श्रीवास्तव सर आर यू देयर सर उनको उनको बनाओ को होस्ट बनाओ सो या बना दिया सर गुड मॉर्निंग सर आई एम सॉरी आई कुड नॉट see you, and since it is already very late and
to play this one. I tried it. FaceTime.
yeah we you can start sir.
Okay. Hello. Can you hear me?
You are audible. We are able to hear you.
Okay. Now where is my talk? Oh, yeah. 1 second.
Yeah, please, sir.
1 second.
So first of all, I should thank you, sir, for your kind blessings.
No. Let me get my talk here.
Yeah,
yes.
Please, sir.
This one. Yes. Okay. So 1 second. Should I share it? They should have.
Yeah, I think it will be better for your synchronization if you can share it.
Okay. 1 second.
So there is a button below which it has an arrow written as share.
Yes. 1 second. 1 second.
When you will press that, it will ask you for the screen. So put it as entire screen.
Yeah, just 1 second.
Share is here, no?
Yeah. Let's try.
Now you're being seen now.
Yeah. Okay. So we go full screen, view, full screen.
Yeah. Now you start presenting your PPT.
Yes. Sir, good morning.
Ask if they see you.
Can you see me, sir?
Yes, sir. Yes, sir. We can see you.
Okay. Thank you very much. I would like to speak about very high energy cosmic ray particles from the Kerr black hole at our galaxy center. It is obviously a very exciting topic, and it is based on some long-going work that started in 2016 with Widom, Swain, and Reddington. This was in Boston, and then continued later on with my colleagues in Perugia, Italy, Imirzi, Panella, and Simone Pacetti. So, okay, and we have our first paper was in 2016 on the subject, which had to do with the maximum force in general relativity and what does it imply. An earlier paper was about the wild cosmic strings that, if I have time towards the end, I will say a few words. And then there are two recent papers about the Kerr black hole as a pivotron at the galaxy center and the very high energy cosmic ray. So these last two are the main subject for the moment. Now, so once again, to repeat, the supermassive black hole at the center of our galaxy, is it the highest energy particle accelerator in our galaxy? So, and therefore, the obvious question, thus, could it originate high energy cosmic rays? Something we have been trying to find an answer for over 100 years. Now, our answer theoretically is yes, under two hypotheses, as I will describe. Luckily, two experimental groups, Hess and Hawk collaborations, claim there is a pivotron proton on the surface of our own supermassive black hole at the galactic center. Then lastly, I want to talk about one-dimensional filamentary structures, very long. They are called lots of names, cosmic strings, or they can even become two-dimensional domain walls. They exist as defects in the uniform Higgs condensate medium after electroweak phase transition. But let me get to it by and by. Now, so first question, where does the mass of a black hole lie? Is it on its surface or is it distributed in the volume? So let's take the simplest system. Suppose I have a spherically symmetric celestial object which has a total mass parameter m, and if boundary is specified by its radius, let's call it r sub g. Now, if there is a gravitational collapse, then it will be, and if it is spherically symmetric, then it will become a spherically symmetric black hole. We call the earlier system the S system as a typical star, and in its black hole avatar as SBH. Okay, so because it would be Schwarzschild black hole. Now Schwarzschild comes in, he tells us the mass parameter, lets us define its Schwarzschild radius, well-known formula we all know and teach. Okay, it is 2 times the Newton's constant times the mass divided by square of the speed of light, which is where its event horizon is. Okay, so now comes about the stability. What can we say about the stability? There is an almost rigorous theorem which says that if the radius of our black hole, of our S system is too small. What is too small? It is 8/9/8 of the Schwarzschild radius, then it will in fact collapse. Okay, so these are well-known facts over the last almost 70 years. Now we want to discuss whether the mass is on the surface or is it in the volume. So suppose I have a total number, n sub t, of particles. They are going, I will call them protons, okay? And they are distributed uniformly over a spherical volume or over its surface. The interparticle separation for a volume distribution is well known. You take the volume, you divide by the total number, and you take 1/3 power that defines your length, and you call it basically the interparticle separation. Now, this is if the mass is distributed in the entire volume. Now compare it, suppose you take all the mass, all the protons, and distribute it over the surface. Then it is the area divided by the total number, and you now take the square root to get the dimension of a length. Now, remember, we are keeping the total number of protons is fixed. So how many are there? Well, let's assume they are all hydrogen atoms, so they are protons. Forget about the electron mass for the moment. Then the total number will be the mass of your object, the black hole, divided in units of solar mass, times the total number of protons that are in one solar mass. Well, that is a known number, 1.25, 10 to the power 57. So we know that now we can calculate. We know our black hole, which is at the center of our galaxy, has a mass of about 4 million solar masses. And now you have a very surprising number. If it is on the surface, then the interparticle distance is truly small. It is 6 times 10 to the minus 7 Fermis. And if you remember, 1 Fermi is 10 to the minus 15 meters. So it is we are really talking about very, very small distances. On the other hand, take the same total number, and if we distribute it over the volume, spherically symmetric, then L3, the number now, is 10 to the plus 4 Fermi. Okay, so now you can, of course, these lengths can be converted into energies. So let's call it, what would be the typical energy of a proton if it is distributed over the entire volume of the black hole? You will get a number like 18 kilo electron volts. On the other hand, if all the protons are on the surface, then it is 330 TeV, which is 10 to the 12 electron volts. So we are now talking about that if all the mass of our black hole were on its surface, we would have a veritable source of high energy cosmic rays of energies up to and beyond several hundreds of TeV. So this is the basically remarkable fact that is only true for supermassive black holes. Okay, now, and if the mass is distributed on the surface. So now, why do we start talking about the surface? Why should we talk? The reason we talk about it is because of a very famous Bekenstein-Hawking theorem, which says that the entropy of a black hole is proportional to the area. Let me be very explicit. You call S the total entropy of the black hole. You divide it by the Boltzmann constant, so it's dimensionless. And it is, so this is their theorem, the entropy area law. Some constant times the area of the black hole horizon. So now, what we did, what Widom and John Swain and I did, was we took something from particle physics, Wilson's Nobel Prize, which is Wilson did a loop action for quantum chromodynamics. And it turns out that we were very, very happy to find that we could apply exactly the Wilson argument or his discourse on loop action, which is then proportional to the black hole area. This is rigorous, by the way, okay? And even we could find the constant. What is the constant? It is the maximum force that general relativity says, divide by the constants h bar and c, so that the final answer is c cubed over 4g times h bar. Therefore, now we can go back and say, what is the dimensionless number for the total entropy in units of the Boltzmann constant? It is c cubed over 4g h bar times 4 pi rs squared, which is the area of our sphere. This is exactly to every single factor what Bekenstein, what is called in the literature, because they did it first, Bekenstein-Hawking temperature. So that KBT is h bar c times c squared over 8 pi gm. It's a beautiful formula that they had derived by completely different arguments, quantum mechanical arguments. We have done it in a completely different way, but we have exactly the same result. Now comes a kicker. Professor Tufte, another Nobel Prize, he finds half the entropy, and therefore, since the product is the same, twice the Hawking temperature. We don't. We get exactly the Bekenstein Hawking temperature. I had a long correspondence with Professor Tuft, and I think we understand why he gets the answer he does. Anyway, I shall stay with what we derive, which is exactly the Bekenstein Hawking temperature. Now, how did we get to it? You will see the argument is absolutely very simple. In quantum mechanics, when you do quantum field theory, you say the differential action, call it dW, which is in units of h bar. So if you divide it, is dimensionless. It is equal to, suppose there is motion in the x-axis. So you take dx, the momentum along x, and divide by h bar. So what you will get? You will get dx dpx over h dt, multiply and divide by dt. Now you realize that dpx dt is, of course, the force. So that is F. Now you have the dx times c dt, it is the area, and you divide by the constants h bar c. F is the force. Now you integrate this over space-time closed loop, as I'll show you in the next transparency. Now you go all the way to the boundary of our black hole event horizon, where, and this is the point about general relativity. General relativity says that there is a maximum force which is only at the event horizon of a black hole, and it's equal to c to the fourth power over 4g. Notice it has no masses, anything. These are just fundamental constants. So this is the maximum force in general relativity. Now we can go back to our integrated closed loop action. The action in units of h bar, which is dimensionless. Here is our constant times the area. Now comes the usual trick in quantum field theory. You take the action in units of h bar in the Minkowski space, and you go to Euclidean, it becomes the entropy in units of kb, the Boltzmann constant. Therefore, we find the temperature, 1 over kBt, which is dsde, and these are the constant, and we have the same as the Bekenstein Hawking. Now take a look at this graph. We are considering a particle that is moving along the x-axis. So I have a little loop, which is dx, which is space-like. I have a ctt, particle is going in time. It is going backwards in space, dx, and it's coming down. So here is my little loop. The area is the cross product of dx cross c dt. That is the Wilson loop. Now we just integrated over the boundary of the horizon, okay? And we got our result. So, now what we have learned, that all the action, all the dynamics of a black hole, certainly a supermassive black hole, okay, is on the surface of the black hole. The calculated, we have the energy, the temperature, and mass, angular momentum, everything is on the surface. We don't need to look at inside because all the dynamics is. So now I come to something that, since our host is an expert in metallurgy and metals and so on, there's lots of interest. So it is that a supermassive black hole has all its mass energy on the surface. This implies that a black hole is a perfect mass conductor, in analogy to electromagnetism, where all free charges migrate to the surface of a perfect charge conductor. By contrast, if I take any typical celestial object, stars, galaxies, what have you, then they are akin to dielectrics in electromagnetic theory. Of course, there is a fundamental difference between electromagnetism and gravity in this regard. Why? Because we have, in electromagnetism, we have neutral atoms and molecules, because we have both positive protons and negative electron charges exist. So we can have neutral objects, whereas in GR, all masses are tracked, and only at very specific Lagrange points or such, okay, which are on a set of measure 0, let's say, the oppositely directed forces may be neutralized. So this is what makes a supermassive black hole so remarkably different. Because all the mass is on the surface, okay, and so on. Okay. So now we have gotten a particle physics conclusion, which says that if all the mass is on its surface, we would have a very high energy accelerator with a mean energy of the order of about 300 TeV. This is therefore the powerful source of high energy cosmic rays. Now, if there is a technical problem that some of you who have worked in it would appreciate, is that when we look at various particles that come out in cosmic rays, they have a fall off with energy with some power law. Is called a critical power law. And now we had already done in the past 20 years, basically, that we had explained that the actual numbers we could calculate in a very specific thing, and it has been reviewed by Pankeri and myself in the EPJC in 2017. Okay, and these are the references. I won't go about it. Let's keep going. Now, suppose you ask, what is inside? I said earlier we need not ask what is inside a black hole, but suppose we do ask, what is inside? Now, of course, we have no way of knowing. These are hypotheses. So the physical picture presented here is that as a system is being compressed, in the process of it becoming a black hole, more and more of its mass from within the system is ejected upon its surface, so that at the end of this process, all the mass would be on the surface for a black hole, and all fields would be expelled from within. If this is actually realized, then you see how remarkable the result is, because this says if no mass remains within the volume, then the energy momentum tensor that's on the right-hand side of the Einstein equations goes to 0 for all values of r less than the Schwarzschild radius. And then the Einstein equations inside would read r mu nu equals 0, as in the true vacuum, and therefore we would expect that g mu nu actually turns to eta mu nu, the Minkowski metric. But if you see, if there is no singularity at the origin, which is one of the most worrying thing about general relativity, what happens to this singularity? So if there is no singularity because there is no mass at r equals 0, then most of the non-physical consequences arising from the famous Hawking-Penrose theorems, okay, that all physics breaks down and all of that may be avoided. I'm saying are avoided because we are, okay. Now, let's just take, what are a few takeaways about SMBH at the Cosmic Center? First, that is a perfect mass conductor with all its mass on its surface. Then, as I have repeated several times, this leads to an extreme surface packing of nucleons, raising their energy enormously, turning them into a pevotron source of cosmic rays. Pevotron just means 10 to the 15 electron volts. Now, the experimental evidence for this has been provided by two experimental groups by looking at photons, by looking at very high energy photons. So therefore, since we observe our SMBH through photons, which are the carriers of light, I have actually suggested that we start calling it a bright hole rather than a black hole, because a black hole was at the time when we are supposed to get no light from it. But if we get the brightest light from the center of our galaxy, I think we should start. We can keep the same initials, BH, but we should start calling it black hole. And the last is the Wheeler's theorem. Namely, Wheeler's point was long time ago that all we can observe about a black hole is its mass and its charge and its angular momentum. And all we are saying is it's absolutely true, but all of it resides on the surface. So that is these are the takeaways for this. Now I want to change the venue of what I'm talking about. Being a particle physicist and working in cosmology, I want to now talk about cosmic consequences of the standard model, the absolutely standard model with the Higgs condensate. Now, there are many things that I won't go over. I just want to emphasize that the standard model has several several conspiracies, let's say. Jaeger-Lerner, around the year 2014, he showed that there is a conspiracy that the high mass top quark provides a large enough negative contribution to the quadratically divergent Higgs mass sufficient to produce a zero and thereby trigger an electroweak phase transition, okay, around 10 to the 16 GeV. Now, why is it important? Because this is, if those of you who have followed the grand unified theories over the last 50 years will recall that this is the area where our energy scale 10 to the 15, 10 to the 16 GeV, which, as people have always said, that is where all the elementary particle forces act in one form or the other. They actually become unified. Now here, what we are seeing is something that nobody had suspected, which is that it is the top mass, when it is, you run it with the renormalization group, okay, it actually provides a zero, and it actually tells you there is an electroweak phase transition. Now I want to talk about something that is our work, which is that we have two other conspiracies we have discovered. The first is that this standard model masses and couplings are such that in the condensed broken symmetry phase, the system behaves as a type 2 superconductor. This allows for the formation of Ablikosov defects in the present context called cosmic, what is the time? Cosmic filamentary structures, which are called cosmic strings. In other words, the standard model, okay, the way the masses and so on are, it produces cosmic strings, and therefore, if they can join together, you can get two-dimensional extensions, which are domain walls. The second one, which is what I would like to really emphasize here, is the dominance of left-handed fermionic currents in the standard model generates geomagnetic fields that induce Coriolis forces. So let me just take the past 10 minutes to see if I can. Now, I don't want to enter into the very murky field of dark matter and dark energy, but the main point is that these are two things which take us beyond the previously accepted standard cosmological model of the universe. Now, since there is some doubt as to the nature of the dark materials, people tend to model it by scalar quantum fields because it's the simplest thing to do. Now, on the other hand, the standard model gives us a scalar Higgs quantum field that is central to the stability of our standard model of weak electromagnetic and strong interaction. Okay, and we have the U1, SU2, SU3 groups, gauge fields. Now here, I'm going to give you rather strong arguments in favor of the hypothesis that the observed in laboratory Higgs scalar field is at the center of both dark matter and dark energy cosmological observations. The pioneering work on this cosmological hypothesis, discussed employing the renormalization group of gauge field theory, was first carried out by F. Jägerlehner from Berlin. Okay, now, now let's say why I'm saying that in the standard model we have a type 2 superconductor. Because in the standard model, we have a symmetry breaking boson field that is called the Higgs particle, the Goldstone Higgs. Okay, and it has condensed into mean order parameter, the energy, which is the vacuum expectation value, and it turns out to be 246 GeV. Through it, we have a Fermi coherence length, which is roughly 8 times 10 to the minus 17 centimeters. Okay, that is much smaller than the London field penetration depth, lambda, defined through the inverse vector boson masses, which are only around 80 to 90 GeV. Therefore, these numbers allow us to deduce that we have domains as in type 2 superconductors. What happens in type 2 superconductors? That there are defects in the otherwise ordered Bose condensate condensed state that take the form of a Brikosov one-dimensional vortex filaments. Now you see what we are doing. We are taking the standard model, we are going into cosmology, and we have got cosmic strings, which are calculable using the Higgs parameters. This is what is so remarkable. So therefore, in the Higgs condensed vacuum, we expect long filaments of cosmic strings of high mass per unit length. Because remember, these are one-dimensional. So you take the total mass and you divide by the length, and that is the mass per unit length of these long filaments. Now, these cosmic strings form the basis of the so-called dark matter affecting the stellar velocity profiles in certain galaxies. Now, first, I will show it to you in Newtonian theory, how it works, and then we can go back that edge immediately after Schwarzschild's spherical solution of the Einstein equation, while Hermann Weyl, the great mathematician, okay, just 1 year later had found exact solutions for high mass per unit length strings, possibly black core if they become black. Okay, so let's see what happens. Now, I won't go over trying to, okay, anyway, let me just say that while the large-scale structures occupy a small volume of the observable volumes, but show coherence on large length scales comparable to the size of the surveys that we have heard, for example, this morning. The web of the filaments also give rise to great voids in the cosmos. So certain galaxies that we consider here are located along long, thin, quasi-one-dimensional filaments. The filaments may then form into relatively flat nets or walls of an approximately quasi-two-dimensional nature. We are here suggesting that the cores of these filaments may be made up of Higgs field vortex lines not in and by themselves clearly visible, i.e. they are thin black cylinders that can become visible due to dust and stellar matter attracted to the vortex filament from the outside. These long vortex filaments play the role of dark matter in that they affect the velocity profiles of galaxies attached to them, but may also in principle be formed into closed finite filament loops within a galaxy. Now, I will show you two sets of pictures. One with the filament pictures that they show is the ESA NASA Herschel project, and then the observable matter form a grand cosmic web hosting galaxies and clusters. Intergalactic filaments are typical of the large-scale structure of our universe. Now, this is the Herschel view, what I'm showing you, of the intergalactic, I think it's called G49 filament, found within the Milky Way galaxy. So this is within our own galaxy. And then there are, if you look at a galaxy clusters, which has this big name, is highly elongated. You see around here that the brightest member galaxies appear round and yellow in this ESA NASA Hubble image. The galaxies align attached to an intergalactic filament. They are here viewed as a standard model cosmic vortex string. The Higgs field determines the vortex nature of the string. Big words. Let's see if we can actually show something about it. Now, the general currents in the vortex. In the standard model, the axial vector current density for a given fermion species is well known to be given by J mu 5, that speed of light times psi bar gamma mu gamma 5 psi. And the full current of the species, of course, is just psi bar gamma mu psi. Now you look at the spatial component of the chiral current density, which is vector J5, and this is, after a little algebra, you find that J5 is the mean value, the total spin per unit volume, apart from the constant C and H bar. Okay, so that is what the theory tells us for every fermion that we have. Now, as we well know, that the standard model is predominantly left-handed nature. And this, therefore, gives us, this has made us suspect that there is a strong possibility, if not yet a proven necessity, of having a chiral supercurrent J5, or equivalently a total angular momentum density S, that includes the angular momenta of all the constituent particles. Now, so let's just do first a simple Newtonian theory, and then we'll do the full GR. Okay, so let's say for the static non-relativistic Newtonian gravitational acceleration field G, for a given mass density rho, we all know G has no curl. Divergence of G is minus 4 pi G rho. G is minus grad phi, and then del phi is 4 pi G rho. So that's Newton. Okay. Now we go one order beyond relativistic, which is 1 over c. And what we find is geomagnetic acceleration field B related to the mass current density J, namely div B 0, curl B is, apart from some constant 16 pi and G, is J over C, and B is curl A, div A 0 in this gauge, and del A is 16 pi G J over C. So this is in going one order beyond and keeping the first relativistic correction. Okay. Why doesn't it go? Yeah. So now you can ask, suppose I take a test particle of mass m and we put it in this static acceleration fields G and B. Then just like in electrodynamics, you will get that the force is the mass times the acceleration, the Newtonian acceleration. But now we have an extra magnetic field type term, 1 over c v cross b. Now we can write down the non-relativistic Lagrangian, mass 1/2 v squared plus 1 over c v dot a minus phi, just like in electromagnetism, except the charge has been replaced by m. Now, equation of motion, the acceleration dv dt is g plus 1 over c v cross b. The first term is, of course, the Newtonian term, the mass term. But look at the second term. The second term is 1 over c v cross b, which we can write as 2 times v times an angular velocity. And this is the gravitationally induced Coriolis acceleration. Now, the Coriolis type gravitational acceleration is running at an angular velocity, omega, which is the vector b over 2c. Now, since the mass current is related to the spin current, that 2J is curl S, you see, we have therefore del of A, the potential, let's call it, is 8 pi G over C, curl of S. Now, to solve it, you define a Hertz potential, A is curl Z, you go through the algebra, and A, the one you want, is minus 2G over C curl integral of the spin over R minus R prime. Now, B is curl A. The potentials phi and A determine the rotational forces on galaxies bound to dark. 1 second. Let me move this fellow here. Yeah, matter cosmic string. Vortex cosmic string gravitational potentials for a mass per unit length mu and a spin per unit length sigma. Notice we have got one-dimensional structures. So now we are talking mass per unit length and spin per unit length. So phi has, and now you have this logarithm, which is the perpendicular distance with respect to some length scale, and the Hertz potential, if you like, is 4G over C times the spin times the same log. So G, what we are interested in is minus grad, it's equal to 2G mu n perp, the vector, unit vector, divided by R. And A is curl Z, so that the B field, which is what we are interested in, is 4G sigma over C R perp squared. Therefore, now we have that the total force on our test particle of mass m is equal to mass times the usual one minus, not usual, minus 2G mu n perp 1 over R plus a 1 over R squared. Okay, now this is coming because we had left-handed currents of the standard model. So for motion within a plane placed, I won't go through this because what it says is that suppose I have a string and I have a test particle, some star say, okay, then it accelerates into this string. That is the Newtonian term, the first one. And the second term, of course, causes rotational motion to the test particle that is falling into the string core. The rotational angular momentum tends to be aligned to sigma, the spin angular momentum per unit length of the vortex cosmic string. This seems to be valid for spiral galaxies. Now, fortunately, I won't go over the whole discussion, but Weil had the exact metric, what is called the axially symmetric Weil metric, which was done in 2000. So it's done in terms of two functions. The U function, well, really it should be three. U, a length parameter A, and a parameter nu. And so he solved the Einstein equations, and these are the equations. They look very ferocious, but actually they are not. They are actually very good equations to look at. And it has an exact solution, which is right here. It's the exact solution of all of these. What it says, that if rho is your radial coordinate, okay, or the axial coordinate, okay, then beta is your constant. It's 2G mass per unit length over C squared. And this is an exact solution to the Weil cosmic string. Now, again, we put a test particle, so the Lagrangian for it would look like minus mc squared d tau dt, which of course is the usual square roots and so on. Now take the non-relativistic limit, because that's what we want. Then you do the thing and you get L Newton. The first part should not disturb anyone. It's 1/2 m rho dot squared, rho squared, phi dot squared, the rotational part plus z dot squared. And now you have the surprise. It's minus 2g m mu log of rho over c. So that now we have circular orbits, for example, simpler case, it's z dot equals 0, and we have a centripetal acceleration that is exactly calculable. It is v perp squared over r perp, which is 2g mu over r perp. Now you have the famous thing. These give rise to circular velocities. V infinity squared is 2g mu, independent of the radial distance from this string. Remember, that's what everybody wants the dark matter to do, is to provide you an asymptotic velocity that does not depend upon the distance. Here, for a cosmic string, rigorously, you find it is true. So now we can also try to do an estimate what numbers we get. So we have the standard model. So we have a phase transition that is, let's say, with some mass scale, 10 to the 15, 10 to the 16 GeV. Then the mass per unit length is essentially m twiddle squared c over h bar. So V infinity over c would be square root of 2gm squared over h bar c. And what we find is about 10 to the minus 3, which is a very satisfactory number that I discussed before. Okay, so this is a very important, in our view, result that should be really looked at more carefully. And now let me just finish by saying that successes of the standard model are by now legion, and as more and more precision tests have confirmed it even further. For example, G minus 2 of the muon is very much under control. And as Jäger-Lehner has forcefully stressed, we already have in-depth tests of the quantum structure of the standard model through large variations of the fine structure constants. Alpha depends on S, alpha strong depends on S, and the large top Yukawa coupling, YT squared, that affects the parameter rho in the weak interactions, that gives us subleading corrections, which are 10 sigma deviation from the leading order SM prediction. Thus, the standard model is on very solid ground, better than anything we ever had, especially since no new physics beyond the standard model has been seen in any of our laboratories. However, astrophysical results have been interpreted in terms of dark matter and dark energy that seems to be beyond the standard model. So that will literally finish now. So now this is where CERN becomes crucial. We need, since we are using renormalization group all the way to the Planck mass or close to the Planck mass, we need very precise values of W and top, so that, and they can only CERN can provide it, whether SM can be safely extrapolated to the Planck mass, and thus provide the very important link between particle physics and cosmology. The verification of an electroweak phase transition around 10 to the 15, 10 to the 16 GeV, and our discussed filamentary cosmic strings and domain walls predicted by the presently known Higgs and weak boson mass measurements. And then lastly, what I started with, which was BH, the black hole, supermassive black hole, considered as perfect mass conductors as sources of high energy cosmic rays. I thank you very much for joining and for your patience in listening to me. Thank you very much. Hello?
Sir, thank you very much to you, sir. And not only to you, but I can see that ma'am is also there. She is helping you.
Yes. This is my wife.
Yeah. So it is very late. If I can see her and I can say thanks to her.
Okay.
Because it is too late, ma'am.
Yeah. Okay.
Actually, we are inspired by your spirit. Being a senior citizen and a veteran in our fraternity, still you are trying to contribute. It is a motivation for all of us, those who are present here. Thank you very much, sir.
Thank you.
Whenever is possible, next time, please do visit Jaipur. And whenever it is possible, it is an invitation to you to visit our university and bless us.
Okay. Thank you.
Thank you, Professor, sir. And I'm sorry that because it was done in hurriedly, so I cannot speak about you. I want to introduce you in front of the participants. Professor Srivastav is Emeritus Professor of Physics, Northeastern University, Boston, Mass, USA, and affiliate to Center Ricerca Enrico Fermi, Roma, Italy. Sir, if
Yeah.
I'm not pronouncing correctly.
No, it's fine. It's
Yeah.
fine.
So Professor Srivastav is an esteemed theoretical physicist and Emeritus Professor of Physics at Northeastern University, Boston, USA. He also holds an affiliation with Enrico Fermi Center at Rome, Italy, and has long-standing collaborations with INFN and the University of Perugia, Italy.
Yes.
With a research career spanning over 5 decades, Professor Srivastav is widely recognized for his contributions to high-energy physics, quantum field theory, and particle physics. He has published extensively on the interactions of elementary particles, and his scholarly work is well represented in the INSPIRE High Energy Physics database. While much of his earlier research focused on fundamental aspects of quantum theory and particle interactions, his recent interests have expanded to include black hole physics and astroparticle phenomena, particularly exploring the idea of black holes as pevatrons, potential source of extremely high energy cosmic rays. Since joining Northeastern University in the early 1970s, Professor Srivastav has maintained active collaborations across the US and Europe. Though now retired from formal teaching, he continues to contribute to theoretical physics through his affiliations in Italy, reflecting a lifelong commitment to achieving the frontiers of knowledge in fundamental physics. Sir, thank you very much for being with us and bless us. So,
Thank you.
people like you are inspiration. So, where are you situated now, sir? This is
I live in Rome.
Rome.
With
Oh,
my
I
family.
have
Rome, Italy.
I have visited, sir, Padua, and the I think you know the department where Galileo worked.
Yes,
Padua,
yes,
Padua is the place, and I have
yes.
been with Torino group also.
Okay,
Dovesi,
Yes, yes.
I was there. We used crystal code while I was doing my PhD.
Okay.
I
Okay. You have knowledge.
I was offered postdoc from both Padua, Professor Silvasari and Professor Dovesi. Both offered me simultaneously. Professor, I think you know Professor Peter Fullday from Max
Yes.
Planck Institute. He was also an theoretical physicist. He worked in electron correlations.
Yes.
He also offered me to be with them.
Okay.
So,
So you know Italy.
yeah, I know, sir. I have been
Okay.
there for 1 month. My first visit to Europe was mostly at Italy.
Okay.
And these 3-4 places where I have been there, and Professor Dovesi, it was for the first time that Professor Dovesi offered me, after interacting with me for 2-3 days. One day when I was taking my lunch, he came to me and offered, Yogesh, can you join my group? So मैंने जैसे ही सुना मैंने सोचा मैंने कहा ये मैंने तो सर को but somehow teachers identify the students. So
Yes.
I'm blessed that people like you, they are always showering their blessings, and that is why we are also able to do something. Thank you very much, sir.
Thank you.
And now we invite Dr. Varun Raghunathan, sir. Sir, can you hear me?
Yes, I'm able to hear you.
Yeah,
Thank
welcome,
you.
sir.
Thank you.
Professor Dr. Varun Raghunathan is Associate Professor at Electrical and Communication Engineering Department at IISc Bangalore. He is an associate. He specializes in photonics, nonlinear optics, and optical communication. His multidisciplinary research group also explores integrated nanophotonics, biophotonics, and quantum communications, bridging fundamental science and applied technology. Dr. Raghunathan earned his PhD in electrical engineering from UCLA in 2008, where he focused on silicon photonics and went on to complete postdoctoral research at the University of California, Irvine, specializing in nonlinear optical microscopy. Before joining IISc in 2016, he worked as a research scientist at Agilent Research Laboratories, contributing to industrial R&D in photonic system. He was promoted as associate professor in 2022. His research contributions span from the development of integrated photonic devices using emerging materials like 2D materials to multiphoton microscopy for biomedical imaging and infrared spectroscopy. His group is also active in quantum communication technologies, including quantum key distribution and device development for next generation quantum network. In recognition of his impactful research, Dr. Raghunathan received the IISc Research Award in 2025, highlighting his contributions to advancing the frontiers of photonics and quantum technologies in India. Sir, we welcome you, and now the
Thank you.
platform is yours.
Thank you very much. Let me quickly share my screen. I hope you are able to see my screen.
Yes, sir.
Okay, very good. One second. Okay. I hope you are also able to see my slides.
Yes, sir. Yes.
Okay. For some reason, I'm not able to see my slides. One second. Okay. So let's get started. So thank you very much for the kind introduction and the invitation to give this talk here at the conference. I wish all the attendees and organizers a very fruitful event as well. I'm going to digress a bit from the other talks in this session and the previous one. I'm going to talk more on engineering aspects of quantum technologies. And more specifically, I'm going to talk about quantum communication research and development. My group, in the Electrical Communication Engineering Department at IISc, is called the Applied Photonics and Microscopy Lab. And the main focus of our work is on experimental optics and building optical systems for various applications. We have been, since my PhD days, last more than 20 years, we have been working in the area of nonlinear optics, working on new materials, right? One area of nonlinear optics is to explore interesting materials which I can use to study nonlinear processes. And in that context, we have been looking at layered materials like 2D layered materials, artificially engineered structures such as metasurfaces and so on. And in the application side of things, we have been using them to do biomedical imaging and so on as well. And in terms of the context of building optical systems, we have been working on visible light communication. There was a lot of interest in India as well for the 5G and 6G communication technologies, where not only the RF and wireless is popular, but also there is interest in looking at alternate communication access technology. And that's where visible light is also seen as a promising option. And also we all work in the area of quantum key distribution, which is going to be the main focus of what I'm going to talk to you about today, basically. Right. So these are the quantum photonics research which happens in my lab. So some of this work I'll be touching upon in this lecture. The first part of the talk, I'll be talking about QKD system development and field testing. So I'll talk about first basics of quantum key distribution and then move on to two specific protocols we have worked on. One is called as the coherent one-way protocol, and the other is measurement device independent QKD protocol, MDI QKD protocol. We've also been looking at how to transform some of the bulky systems we have in the lab spreading across optical tables to miniaturize chip scale components. So I'll talk about some of our effort on photonic integrated circuits like PIC development for the QKD application. And more on the research side of things, we have been looking at alternate material platforms which will be good to generate quantum light sources, more specifically entangled photon sources using spontaneous parametric down conversion type processes, where we are looking at metasurfaces like gallium arsenide, aluminum gallium arsenide metasurfaces, molybdenum disulfide disks, and so on. This is more on the base or the applied physics side of things. We are also exploring applying quantum light sources to do microscopy experiments with the goal of seeing if we can improve the performance better than what a classical microscope system would provide. More specifically, we are looking at second harmonic multiphoton fluorescence type processes and applying some of the photon pair sources we can build to improving the performance in terms of sensitivity, resolution, and so on. So due to lack of time, I wouldn't cover the part 3 of the talk, but mostly focus on part 1 and 2 as part of this presentation. Right. So what is the grander goal of building quantum communication technology is to have interconnected resources. For example, it would be good to have quantum internet, right? So what is a quantum internet? Quantum internet is something where you have different quantum resources which are interconnected through some communication links, right? So these quantum states of light or quantum states of any matter qubit or any of them have to be reliably transported from one node to the other for this kind of an network or quantum internet to be enabled, basically, right? So then one could envision in the future, right? Right now we are not in a stage where we can say that this is done and dusted, but we are slowly kind of working towards like having interconnected quantum resources. And towards that goal, we would want to have quantum computers, quantum sensors, quantum key distribution networks, everything interconnected through reliable quantum communication resource, right? And then one more point to appreciate is that quantum internet or quantum networks cannot exist by themselves standalone, right? There needs to be classical infrastructure also, which needs to coexist along with this. So this is taken from a paper where the bottom layer is where you have the quantum layer, right? That is the file layer, the physical layer to do quantum communication, but only that is not sufficient. One has to have classical resources to do communication. So one has to exchange clocks, one has to reconcile whatever was transmitted, make sense out of it, calculate errors. A lot of other tasks are there where a lot of classical communication is also involved. And on top of that, there will be access layers also, where people would want to access the quantum network. How do they get time in that quantum network? Is through some access reconciliation and all that. And above that will be the application layer, right? I'm trying to communicate securely, for example. That would be the application. So that there's a lot of classical and quantum which needs to coexist for a quantum network to be enabled, basically. So it's not only quantum, but classical and quantum needs to coexist if one has to envision building such kind of quantum networks, right? That point needs to be appreciated. Then if we are working towards building a quantum internet, then what are the different quantum technologies which are required to enable that? So here we have kind of listed out few different functionalities. As you go from the bottom to the top, they increase in complexity. Some of these tasks have already been figured out. Others are on very early stage of research, basically. So on the left-hand side, there are these few different technologies or quantum technologies which are required. Like, for example, trusted nodes, right? Trusted repeaters are useful if you want to do cryptography you want to transfer information, quantum states securely. You can transfer them from one node to the other, relying on the security of those nodes. So they are trusted in that sense. And then on top, there are prepare and measure type schemes. I will explain what these are in the subsequent slides. There are also entanglement-based schemes which are available. Then eventually, one would want to store quantum states, for example, matter qubits, ion qubits, the spin states, all those need to be stored. So one has to have reliable quantum memories where these can be stored. And then do operations which are fault tolerant, right? There could be errors which can occur, but as long as we are able to build enough redundancy or have some mechanism to figure out there has been an error and correct that, then that will really help in doing fault-tolerant computing and eventually have networked quantum resources, right? That is the top of this food chain, basically. Then what are the applications they are enabling? Trusted nodes enable quantum key distribution. Trusted nodes and prepare and measure enable quantum key distribution. Entanglement-based schemes are useful if you want to do quantum sensing, if you want to build quantum repeaters, quantum teleportation. All those are important functionalities where entanglement sources are essential. Even for quantum cryptography, there are protocols which rely on entanglement as well. And then when you have quantum memory, I can store states, retrieve them, and do processing. So that would be essential. If there are latencies which are there in these networks, then it's always good to have some reliable storage mechanisms as well. Then eventually you will want to do distributed computing as well with these kind of networks. And then there are more advanced applications which can be tried out as well in these kind of networks, which is shown at the top of the food chain on the right-hand side. So how are we in terms of what is the level of maturity here? So at that, I have ticked some of these on the right-hand side. So right now, we know how to build trusted nodes, do quantum key distribution, quantum communication like quantum teleportation protocols or quantum repeaters are all having tried out in labs, very high-end research labs in Europe and all they have tried out. There are very good papers which have been written, but then it's still not at a stage where I can deploy it in a real network yet. So there is still a lot of work that needs to be done. And then eventually there's also parallel effort in building quantum computing resources as well. And eventually these will be connected to do distributed quantum computing. So we are looking at another 5 to 10 year time frame where some of these other tasks which are shown in the top of this food chain will also be realized basically. So this is to just give you a quick glimpse of what a quantum internet would require, what are the applications they support, and then where are we, right? What is the report card for that? We have tried. Some of these are a lot more mature. The bottom 3 are definitely mature. The top 3 are still where a lot of work needs to be done. So with that context, I'll move on to the Indian ecosystem, where recently I think there's this National Quantum Mission which got started. There are multiple hubs which have been identified for different verticals in the area of computing, communication, sensing, and materials. And I work as part of the Quantum Communication Hub. The hub is located in IIT Madras, and we are member institutions. We work with them on joint projects. So in terms of the deliverables which are required for that, these are some of the deliverables. There's a requirement to build satellite-based free space communication across distances of 2,000 kilometers or longer, basically. And then have intercity quantum key distribution of similar kind of distances, 2,000 kilometers, with trusted nodes, basically, and using existing or separately deployed fiber resources for this. And then eventually take some steps towards building quantum networks with multiple nodes which are connected with quantum memory and suitable entanglement swapping functionalities, where multiple nodes, at least 2 to 3 nodes, have to be connected to show that we are taking some small steps towards building a quantum network. So these are the expected deliverables. And as part of some of our effort in IISc, we are working on 2 projects. One with the IIT Madras Technology Hub, where there is interest in interconnecting between Chennai to Delhi. And we will be working on the Bangalore nodes for this, and also try out some of the new protocols which we have been testing out in the lab and so on. And then we also work with IIT Delhi in building PICs for doing entangled photon generation for some of the entanglement-based protocols they are interested in trying out. Right. So this is kind of a bigger picture of quantum communication as per the India's National Quantum Mission, and the kind of things we are contributing towards that as well is listed out here. Right. So then moving on to more technical stuff, when you talk about quantum communication, you are relying on basic principles of quantum mechanics to do communication. So what are they? This is for the interest of the students who are in the audience. Quantum states can be represented by superposition of basis states. So I could have a state get 1, get 0, or get 1, and then I could have superpositions of them with relative phase and so on. And whenever I do a measurement, this state would collapse to one of these basis states. And then when I repeat these measurements, then I can find a distribution basically. And with some probability, it would collapse to a basis state. Then there also exists what are known as entangled states, which have stronger than classical correlation, which can also be leveraged to do interesting operations, which there's no classical counterpart to that as well. And the other key property is that quantum states cannot be cloned, which means that if I try to clone it, I would destroy this thing, or I would modify it, or in the worst case, if there is 2 parties who are trying to communicate through quantum states, they will be able to know that I'm trying to tamper with this quantum state, basically. So these are some of the basic tenets which ensure that there is going to be security if I want to do quantum key distribution. And more specifically, when I try to do quantum communication, it's rather understood that photons are the best way to do this kind of communication. The reason being that you can generate a lot of them on the fly. Right? Memory for photons is difficult to achieve, but then I don't have a dearth of photons. I can generate multiple of them in different quantum states, like single photons, entangled photon states, weak coherent states, and so on, and then leverage their different degrees of freedom. By that, I mean I can make use of their polarization property, frequency, wavelength, time of arrival, and so on, to encode information. So I can encode polarization states like horizontal, vertical, diagonal, anti-diagonal, and so on. In terms of time, if I have optical pulses, then I'll be able to encode them like early time, late time, and so on as well, right? So these are the properties I want to leverage in the light so that I can encode quantum states and transmit them. And then they don't decohere that easily because I will be able to preserve that state and distribute them over long distances, right? That's the property which is very attractive, because if I work with matter qubits, it can easily decohere based on the environment it is in, and I can lose that state rather easily. But here I can transmit information over kilometers of distance without losing that property, basically, which is what is desirable if I want to do quantum communication. Right. So then when moving on to more specifics about quantum key distribution, here we want to make use of quantum mechanics to ensure that I can do secure key distribution so that two parties, for example, Alice and Bob, want to talk to each other. They want to do this securely in the way that if there is an eavesdropper who is tapping into the channel, he would get no information, and Alice and Bob will be able to successfully transmit the key, right? So what this guarantees is security for communication. And where this would be beneficial is like a lot of classical cryptography schemes right now are based on computational complexity, right? By that, I mean, like I take two prime numbers, I multiply them, and then try to generate a key with that, basically. Do more processing and then try to generate the key. But now there are quantum algorithms which are coming up, which can be implemented in the not so not so distant future, that one could think about breaking these products into their prime factors, basically, right? So these can be done in polynomial time scale, which seriously poses a threat to existing classical cryptography solutions. So that's where if you had something which is guaranteed to be secure based on laws of quantum mechanics, then I can make sure that whatever is being transmitted is really secure without any eavesdropper getting that information, basically. And broadly, these schemes are being classified into prepare and measure. By that, I mean Alice prepares some state, Bob measures the state, and then they do some reconciliation operation subsequently to ensure that they end up with a common key. They also have ways in which they can subtract out Eve's information in a way that they end up with a unique common key, which Eve has no information about. Right? So this is a prepare and measure type protocol. There are also entanglement type protocols where there could be a source of entanglement, which could be with Eve even. Right? And then one photon gets transmitted to Alice, another photon gets transmitted to Bob. Then Alice and Bob do some measurements. Based on the outcome, they know exactly what they have obtained. So correspondingly, they know what Bob would have obtained, basically. This is a property which arises because entangled photons are strongly correlated, more than classically correlated, that if I'm able to prove that this source preserves its entanglement, doing suitable tests, then I know that Eve has not tampered with that source. And then I can successfully transmit information between the two parties, basically. These are entanglement-based protocols, and they can be made device-independent also. By that, I mean, they are not, as long as we are able to show that that box which is generating the photon pairs is really generating entangled photon pairs, then it makes it device-independent. Any device which is used for it can be used for doing the measurement, basically. That's the idea. Right? So then at the bottom, I have listed out few examples. I'll go through some of these protocols. The BB84 and COW is something I'll go through. The T12 is something I may not have time to cover. And similarly, in the case of entanglement, there is what is known as Eckart 91 protocol and BBM 92. Right? So in all these things, the first two letters are for the scientists who came up with the protocol, and the last two numbers correspond to the year in which that protocol was proposed, basically. So BB84 was Bernard Bressart in the year 1984. Right. So moving on to more details, this is also a little bit more forward-looking. This is just to show you the recent trends in quantum key distribution. I've already explained to you the prepare and measure protocol, where Alice and Bob try to communicate through a quantum channel. There's also a classical channel, which is used for various clock distribution, synchronization, and also reconciliation. Like Bob would want to reveal the outcomes, and then based on that, Alice and Bob would agree upon a common key without revealing that in the public channel, basically. That's the idea, right? So then when we work with photons, right? The benefit of working with photons is that this is a mature technology. There's a lot of effort already being placed in building photonic systems, for example, for doing telecommunication, right? There's a lot of fiber resources, fiber components, high-speed modulators, lasers, everything being built that I can leverage that to do quantum communication as well through fibers. So I would like to leverage a lot of the telecom components and the infrastructure to build my quantum communication link. Similarly, in the case of visible and the shorter near IR, there are a lot of mature technologies which are already available, like photomultiplier tubes are available. People are already building single photon sources in the visible range and so on. I would like to leverage that to build free space quantum communication system as well, right? So I would like to leverage the existing photonics hardware and infrastructure which people have built over the last multiple decades to build my quantum communication system, right? There are also some disadvantages to building this using photons. I'll come to that a little later. But then I'll also tell you what are the current research trends. That's also important to know. There's interest in enhancing security, right? Eavesdropper will always try to find a way to tap into the channel, right? Like, for example, an eavesdropper can put a beam splitter and tap into the quantum information being transmitted between Alice and Bob, right? So then I need to come up with better and better protocols which are much more secure. And that's where people are looking at other device-independent protocols, including us. So I'll talk briefly about measurement device-independent protocol in the later slides, basically. There's also interest in extending the distance of communication. Typically, the distances where prepare and measure is tried out is like 300, 400 kilometers. But now if I can go to 1,000 kilometers, 2,000 kilometers, then I'll be able to connect between multiple cities, right? For example, one could now think about connecting between Bangalore to Delhi kind of distances with a single transmitter, single receiver, if such kind of a link can be established. So people are looking at protocols which offer favorable length scaling as well, where these kind of twin field and measurement device independent protocols are being looked at, right? So then there's also interest in pushing data rates higher and higher for shorter distances as well, right? Then I would want to have protocols which probably don't worry that much about the security aspect, but then try to guarantee better data throughput, right? So there are protocols like that. Cow protocol is one such protocol, which I would discuss about in the subsequent slides. And obviously, fiber resources are also limited, right? So then if there are techniques through which I can make sure the quantum and classical links can coexist, there are some advantages which will come through that as well. So few of these things I'll discuss, like some of the work we have done, I'll discuss subsequently, right? So before moving on to more details about our work, I will also try to highlight the BB84 protocol, right? This is just to make sure everybody is in the same page. The BB84 protocol stands for the people who invented it, Charles Bennett and Gilles Broussard, who invented it in 1984. It was in fact presented at a conference in Bangalore, basically. So we have some connection to this here in Bangalore as well. The way this protocol works is that they start with a light source. Some of the earlier demonstrations made use of attenuated LEDs. Still, people make use of attenuated lasers. Though, if you have true single photon sources, one can guarantee better security in these protocols as well. Then what happens is that there is selection of bases which is done. One chooses between the rectilinear basis, which is horizontal and vertical, or chooses between the diagonal and the anti-diagonal basis. Then one would encode information by selecting a qubit 0 or a qubit 1. For example, the horizontal and the 135 degree is what is considered as the qubit 0. The 90 degree and the 45 degree are considered as qubit 1, right? So at Alice end, basis is chosen, then the qubit state is also chosen. Then it is transmitted over the communication channel, which could be fiber or free space. At Bob's end, what is done is that a basis selection is done, right? That's what is shown here. Either rectilinear or diagonal basis is chosen to do the measurement. If Alice and Bob had the same basis, right, assuming the losses or the scrambling of the polarization state is not going to occur in the channel, then what is going to happen is that as long as Bob chooses the right basis, he would be able to detect the right qubit state, right? For example, if Alice transmitted a 135, Bob used a diagonal anti-diagonal basis for measurement, then he would be able to recover the state 0. If he wrongly chooses the rectilinear basis, HV basis to do the measurement, then what will happen with 50% probability, he will project it to the horizontal basis or 50% to the vertical basis. So then what happens? There is an error which is introduced in the channel because of the fact that there is a basis mismatch between Alice and Bob, right? So then during the reconciliation step, Bob would announce all the bases he had used for doing measurement, and whichever ones aligned with Alice, that's the one they keep. The rest they throw away, basically. That's how the reconciliation gets done. Now, if there is an eavesdropper in the channel who is also tapping into the channel, eavesdropper E would also be making the same kind of measurements as Bob, right? So with only a 50% probability, they will be detecting the state correctly. And then, right, they have to transmit again, right? So the consequence of that is that if there is an eavesdropper who is doing the detection and retransmission, the errors at Bob's detections would increase, right, significantly. Only 25% of the time he would get it correct. Rest of the 75% of the time, there will be errors, basically. So then Alice and Bob, looking just at the errors in the channel, will be able to pick up that something is wrong with that piece of communication, that one has to abort it because errors are very high. Right? That's the basis of this kind of a protocol, where I use single photon states or weak coherent states to do encoding, and the photon which is being detected will come out correctly only if the right basis is chosen. If there is a middle party like eavesdropper who does the same operation, the fact that they are doing measurements and retransmission would increase the error, and that gets picked up by Alice and Bob, basically. That's how this protocol ensures security. Right? There are more advanced versions of this. If I use true single photon sources, then what happens if Eve were to tap into that, then that doesn't get transmitted to Bob and all that. If they use weak coherent sources, weak coherent source is a coherent state which can be written as a superposition of number states. So any tapping into the channel, Bob can go unnoticed, basically. These are known as photon number splitting attacks, which can be avoided as well by including decoy states and all that, right? I'm not going into too much detail. There are different variants of these things as well. As people come up with new and new ways to hack into these kind of communication, the protocol has also evolved to make it more and more secure, basically. That's the idea, right? So this is a variation of that, which is optimized for speed, right? So this is called as coherent one-way protocol. The way this works is that I don't encode the diagonal, anti-diagonal, and the rectilinear basis as 50-50, right? The way that is often done is that horizontal vertical is reserved for doing the quantum communication, while diagonal, anti-diagonal is reserved for doing eavesdropper detection, right? And then I'm not too paranoid about the eavesdropper that I have to do it every so often at 50% probability. I do it only at 10% probability. Then what it means is that I'm kind of compromising on the security by checking for eavesdropper less frequently, and in that process, increasing the key throughput by transmitting more bits through the horizontal and vertical basis, right? That's the idea. More specifically, we don't encode in polarization, but we do time encoding in my lab, basically, right? So this is a setup what we have in the lab. As you can see, it almost occupies an entire optical table where there are waveform generators which are used to transmit the electrical wave or generate the electrical waveforms. There are intensity and phase modulators which are used to encode the time of the pulses. An early pulse will denote the qubit 0. A late pulse will denote the qubit 1. A superposition of them with a relative phase will denote the X basis pulses, which is equivalent to the diagonal and anti-diagonal basis. And then the early and late pulses are the ones which are sampled more frequently to detect the qubit states for the actual communication, while the other bases, the X basis states, are detected less frequently with the goal of just doing eavesdropper detection. And the way an eavesdropper gets detected is that if there is an eavesdropper in this channel, they would perturb the phase between the pulses. That will increase the error when I do the phase measurement, that I'll be able to pick that up, right? That's how the time encoding works. And sometime in around 2022, as part of a MIT project, we demonstrated like 25 kilometers of real fiber where we were able to transmit few kbps kind of data rate, basically, right? So then we looked at protocols which would improve the speed of communication. The way we do that is by doing high dimensional encoding. The way this works is that if I'm limited by the dead time of the detector, right? The detector will always have some time where it's waiting for the detection of photons, after which it takes certain amount of time to reset. Right? This occurs because there are after pulsing which can occur in the single photon detectors. I want to avoid that, right? So if I'm limited by that, then it makes sense to encode multiple bits for the symbol transmitted. So here in this picture, we have shown few examples. If you have qubit transmission, then there are only 2 time slots, an early time slot denoting qubit 0, a late time slot denoting qubit 1. But then if I start increasing to more number of slots, then every time slot can be used to encode multiple bits, basically. What by that I mean, if I want to encode bits, for example, if I want to encode 2 bits, then I need to have 4 time slots. If I want to encode 3 bits, then I will have 8 time slots, right? So what this means is that every symbol or pulse detected gets mapped to multiple bits. Through this approach, I can improve the throughput, right? I can improve the bit rate by doing this kind of pulse position type modulation. There are classical analogs to this as well, but it makes sense to do this kind of encoding provided I'm limited by the detector's rearming time rather than photon arrival time, right? So then we tried this protocol as well in our system. These are some results we were able to obtain. So this is the main conclusion here. So if you have a qubit system, we have been able to achieve like 60 kbps kind of data rate with error rates of about 2%, basically. These are fairly low error rates. Then I do 16 dimensional encoding, like 16 time slots to transmit 4 bits, right? So it's supposed to scale as log d to the base 2. So it is supposed to scale by 4 times. But then in reality, there are also errors which are introduced because of some spurious detection and all that, which needs to be eliminated. So when we eliminate that, we do notice that between 3 and 4 times improvement is what we see, basically. So what these kind of protocols achieve is a better key throughput, right? Which is achieved by opening up more number of time slots to do the encoding. We have also tested some of these protocols in the field. So this is actually the IISc fiber backbone, which we use to transmit between 2 different departments, our department, ECE department, and the Department of Electronic Systems Engineering in a different part of the campus. The total distance is about 3.82 kilometers. The total losses was about 9 dB. Basically, in classical communication, one would not even pay attention to losses because I can put amplifiers and so on. But in quantum, I cannot afford to do that. So then every loss, every dB of loss matters when I do this kind of transmission, basically. But still, we were able to set up the transmitters in the electronics department. So that is what is shown here, the transmitter part of the setup, which occupies almost half the optical table. Then these are on the wall, which is used to connect to the IISc fiber backbone. And subsequently, we were able to receive this in my lab. This is the reception part where we have single photon detectors and so on, and a corresponding box on the wall to receive the signals, basically. And these are some of the results. The main conclusion is that there was slight decrease in the data throughput because the channel losses were more, but nonetheless, we were able to achieve like nearly a 200 kbps kind of data rate with an error of about 6.9%, basically. Right. So the last part of this COW protocol, I would also like to say that we have also tried to combine classical and quantum channels in the same piece of optical fiber, right? So this was a bit of a shorter fiber, about 2 kilometers in length. But the main message here is that one could combine the classical and quantum through the same piece of fiber. What this entails is a careful selection of the wavelengths, right? The classical wavelengths can scatter to the quantum wavelengths through Raman scattering, Rayleigh scattering, and all that. I would want to avoid that. So I want to space these classical and quantum as far apart as possible. I also make sure that the quantum channel is on the blue side of the classical channel to ensure that even if there is Raman scattering, it would be only the anti-Stokes part of the Raman scattering, which would be very weak. Right. Then we have to also optimize on the number of wavelength division multiplexers and all we have in the channel. And subsequently, we were able to demonstrate the classical and quantum link can also be used over 2 kilometers. For this demonstration, we achieved about 8.2 kbps kind of data rate. The same when I turn off the classical channel, having only quantum, we were also able to achieve a similar kind of performance, basically. Right. So one could think about classical and quantum resources coexisting and doing cryptography also through the same piece of optical fiber. Right. So I'll move on to another protocol which we have tried very quickly in the next 5 minutes or so. So what we are trying to do here is the measurement device independent QKD. Right. So by this I mean the eavesdropper can do the measurement, right? But still, what happens is that eavesdropper would know only the outcome of the measurement. The eavesdropper doesn't know which transmitter had transmitted what information, right? So then to set up such kind of a system, These are called as measurement device independent because you're independent to the detectors basically, and that's why it's called measurement device independent protocol, right? So the way that is done is that Alice and Bob could be two end nodes which are transmitting information to a central node, and then the central node does the measurement basically, right? So as you can see, these kind of architectures are kind of amenable if I want to set up star topology, right? By that I mean multiple nodes which are interconnected to a central node. Where this becomes particularly interesting is that in the kind of motivation I gave you, I was talking about quantum networks where different quantum resources are connected to different nodes, basically. So one could envision these kind of architectures being scalable to QKD, quantum sensors, quantum computers, and all interconnected to a central node where measurement happens, right? So looking ahead, one could think about these kind of measurement device independent QKD protocols transforming themselves into quantum networks as well in the future. The way we do this again is through time encoding. Again, I have Z basis pulses, which are an early pulse, which represents a state 0, a late pulse, which represents a state 1, or a superposition of both early and late with a relative phase, which denotes the X basis states 0 and 1 as well. So I have two nodes here, Alice and Bob. Both of them are transmitting now. So then I have my states which are encoded. The encoding part is very similar to the cow protocol I just described. The measurement part is a bit different because what happens is that the quantum states which are transmitted combine at a beam splitter, right? This measurement strategy is very similar to a Bell state measurement or a Hongo-Mandel interference type measurement, where these quantum states come together, they interfere, and then the outcome of the interference is measured using two single photon detectors. The kind of detection events we are interested in are really what are known as singlet states, where, for example, one detector clicks for one particular time bin and the other detector clicks for the other time bin, right? That's what we have circled here in this red dashed ellipse, basically, right? So these are states where D1 clicks in early, D2 clicks in late, or D1 clicks in late and D2 clicks in early. Why? Because Charlie or even the eavesdropper would know only the outcome of the measurement, but they don't know which qubit state or which pulse was transmitted by which transmitter, basically. Because it could be Alice or Bob who could have transmitted the early or late. That is indeterminate at the point of measurement, and that's what guarantees security in these kind of measurement device independent protocol. And again, the X basis is used only for eavesdropper detection by looking at the error. If there is an eavesdropper, they perturb the phase in the relative phase in the measurements, and that can be detected as an increased error. The way that is often done is by doing a Hongo-Mandel type measurement at the central node using weak coherent states, basically. I'll come to that in the next slide, but these are all the possible measurements which can occur, basically. Alice and Bob can transmit Z basis or X basis states. They can transmit Z0, Z0, Z1, Z1, Z0, Z1, Z1, Z0, and a lot of other possibilities are listed out, right? When they transmit the same states, those events get discarded because there's nothing useful you can gain out of that, basically, because two different detectors don't click in that scenario, right? So two different time slots don't click, sorry. So then when I consider the second row, when they transmit different Z basis states, these are still useful because they will always result in singlet state detection. And that's something I can use for my actual qubit transmission. Similarly, when I do X0, X0 or X1, X1, those are still result in HOM interference type process, but then these are not very useful because again, the same qubit states are being transmitted. But what is useful for eavesdropper detection are the ones of the form X0, X1 or X1, X0, which are really kept, which are used for the Hongo-Mandel interference, and they are used to estimate the phase error. If it exceeds a threshold, then it is assumed that something has perturbed the channel that I would discard that block of communication. Then if I had scenario where X0 and Z0 were transmitted or any of those combinations, during the shifting operation, those are also discarded because those are also not very useful. So what is really useful for the qubit detection or transmission is the second row. What is useful for the phase error or eavesdropper estimation is the fourth row, basically, and that's what is retained. So these are some experimental setups we have in the lab for doing the two different laser sources for Alice and Bob, doing the encoding using intensity and phase modulators, transmitting through real fiber spools. The fiber spool part is not shown here, but we have tested this out up to 100 kilometer type distances. And then at the central node, we have beam splitters which do the combining and then single photon detectors who do the measurement. We use both avalanche detectors and superconducting detectors for doing the actual measurement. Right? So then for the X basis states, when two identical states arrive, they're going to undergo a Hongo-Mandel interference. Right? This is something which is known in the case of two indistinguishable single photons which bunch together. And then what happens is that the Hongo-Mandel shows a dip because there is going to be no coincidence detection between two separate detectors because of photon bunching effect. But now I'm working with laser sources which are coherent states. They are not true single photon sources. The consequence of that is that I still end up with some coincidence dip, which shows that there is some probability with which the photons bunch together. But this is not perfect one, right? This is not perfect 100% visibility for this coincidence dip, but only 50% visibility, right? Which tells me that there is some remnant of that single photon characteristic which my weak coherent state maintains, which I'm able to measure by this Hongo-Mandel dip, which is obtained for the weak coherent state. And then the contrast in this dip is what is used really to determine whether I have a good indistinguishable source, basically. The way we do this is by looking at this Hongo-Mandel visibility over long durations in time. We have done this over 5 to 6 hours and get very good visibility in this Hongo-Mandel dip. It also depends on the wavelength. The wavelengths have to be aligned very precisely to within about tens of picometer. If I depart from that, then the visibility goes away. Right? This tells me the kind of characteristic I would need for my laser source to ensure that they are really indistinguishable laser sources, two independent, indistinguishable laser sources, so that I can have this kind of an Hongo-Mandel interference effect. Right, so I'll pick up pace. So we have also done MDI-QKD experiments. Some of the early experiments we obtained about 150 bits per second. Obviously, we are relying on coincidence, so the key rate will be lower when compared to the cow kind of prepare and measure type protocols. But the advantage this brings in is an enhanced security and longer distance for communication. Right, so we have tested this up to about 100-kilometer distance from Alice to Charlie or Bob to Charlie, and still able to obtain positive key rates, basically. Then we also tried high dimensional encoding with this kind of a protocol. Again, if for Z basis, we use multiple time slots to do the encoding. For X basis, we come up with a scheme where we do relative phase encoding between multiple pulses, zero, or the states are mutually unbiased. So when I'm able to do that, then I can do the same MDI-QKD experiment with high dimensional states being encoded in time. Right? I'll skip some of the details, but just present the results. So what we notice is that we are able to do communication by encoding in multiple dimensions in time as well. The best results we have been able to obtain are about 2.8 times improvement for D equals 8 encoding. D equals 8 was about the optimum value beyond which the errors seem to increase significantly, lowering the key rate. So D equals, I'm able to do 8-dimensional encoding. So at least 3 times is expected, but I achieve about 2.8 times. The other interesting thing is that we compared the performance of HD, MDI versus cow. And what we found is that in the case of MDI QKD, the kind of improvement you get when compared to qubit is much higher when compared to the simple prepare and measure protocol. The reason for this is because we are relying on singlet state detection. There are multiple combinations of singlet state which are possible in the MDI case, which are absent in the cow case, basically. Right? And that's what gives rise to this prefactor, which is shown in this expression. 2 times D minus 1 by D is the prefactor in front. And that's what, because of multiple level D coincidences which can occur in the Z basis detection, the overall key rate is better. Okay. So moving on to a few different, more forward-looking, there are a lot of QKD systems which are being built both for research and implementation purpose. I've listed out some different companies here. QNew Labs is a company out of Bangalore. There are many more startups which are coming up recently, both building the components like detectors, laser sources, and so on, and also building systems, right? Using them to build QKD systems. Like even CDOT also has some product they have, which they are testing out in Delhi and so on. There are also many foreign companies who are building these, testing out in real quantum networks. There are also modules which are available for teaching purpose as well. There are companies who are selling these modules, especially for teaching purposes. So I've listed out some of the performance here as well. So the kind of performance we achieve in our labs are very comparable to what has been demonstrated in real products, right? That is one key message here. Right. Another aspect we have been working on are these PIC development. Can I integrate like some of the photographs I showed you, the system is spread across an entire optical table. So this is essentially a chip of like about few centimeter, like 2 by 1 centimeter kind of a distance or dimension, where now we are trying to put all the components, right? Like for example, a laser source will be external to this chip, but the intensity, phase modulator, attenuator, everything we want on the chip so that I can do the qubit encoding on the chip. So we are relying both on external, like foreign foundries to do this fabrication. We're also relying on our own IISc foundry as well to make some of these PIC chips as well. Right. So lastly, I would also like to mention that these QKD systems have been tried out in field deployable networks as well. These are few examples from around the world. The first example here is a Cambridge network in UK. The bottom one is a Chinese network, which they have built from Beijing to Shanghai with multiple nodes. About 30 odd nodes are being set up. They've also tried out different architectures as well to set up these nodes. There's also something in Japan as well. In India also, we are trying to do these prepare and measure type networks. These are two examples. One was tried out in collaboration between DRDO and IIT Delhi, which was tried out over 100 kilometers between Prayagraj and Vindhyachal. This was in 2022. Similarly, ISRO was also trying to do something between their labs in PRL in Ahmedabad and Mount Abu. There was a telescope. They were trying to try this as well. More recently, there were also some reports in IIT Delhi where they have tried free space communication across 2-kilometer distance in their campus as well. Right. So a lot of different demonstrations have come up. So I'll just conclude by saying that quantum key distribution is one important aspect of quantum communication, right? Broader picture is the quantum communication where I want to reliably distribute quantum states. One use case of that is quantum key distribution, which has been one of the most advanced areas in doing any of these quantum technologies, because there I can leverage a lot of the classical infrastructure to do the communication basically. And we ourselves have tried out some of these things, like COW protocol is something I showed you, field deployment in IISc is something I showed you. We're also looking at more advanced protocols to enhance security and distance of communication, which is the measurement device independent protocol. We're also trying how to improve the key throughput here by using high dimensional encoding as well. PIC development is another important aspect we are also focused on. Other than that, my group also works on microscopy type experiments, more on the science side of things, trying to apply quantum states of light to do microscopy. Right? I will conclude here. I think I'm almost on time. I'll stop here. If there are any questions, I'll be happy to take. And thanks for the opportunity to present.
Thank you very much, Dr. Varun. Very nice talk. So
thank you, sir.
It again established, your talk established that the interaction of human with nature remains very intrinsic. We started communicating through light, the photonics.
Light, yeah.
Again, we are coming. I was looking to your the last slide or the last but one. That
yes.
Open 300, I think 300 kilometer communication was established within Ahmedabad and Mount Abu laboratory.
Yeah, 100 kilometers.
Yeah. 100 kilometers. Oh,
correct.
So we are returning back to that, and if it is possible, I think it will revolutionize the communication systems. And although the security of these systems will be very much
correct
to be worked upon. And this is the key area where our students can benefit.
Definitely.
They can work onto these areas and they can gain more.
Yeah.
With the thanks, I will request you to be with us for some time. Whenever you have some areas or in your schedule, when you can spend 2-3 days or more, I will request you for a week stay with us at Jaipur. So that we can plan also, because at IISc Bangalore, you people are doing very many things. We need some more satellite centers like ours. We want to offer ourselves as satellite centers. So if you can guide us, then not many students could connect with these kind of efforts, and we can also try something under your mentorship, and we can also contribute towards the technological development of India.
Yeah, definitely, sir. We'll be happy to help. Do reach out. I'll be happy to.
So thank you very much for being with us. Not only you, but other speakers also from right from Professor Jainendra Jain, then Professor Swaradeep, then Professor Reddy. Everyone was there, and we are very much thankful to you, all of you, that the students who are participating into it, not only who are physically or online participating it, but those who will be able to see these recordings, they will also get benefit out of this. So your investment will, I think, multiply. Thank you very much. And I think now we should end the proceedings today. And we'll meet tomorrow, right sharp at, I think it is around 11 a.m. I have shared the schedule with all of you. And I think it is tomorrow we will start. Tomorrow we will start at 11 a.m. So bye-bye for now, and we will meet tomorrow morning at 11 a.m. Thank you very much, everyone.
Thank you, sir.
Okay,
Thank
bye.
you.
Namaskar.